GCE Advanced Level Chemistry Practical Series Experiment number 23. Test to identify nickel 2+, ferrous, ferric, copper 2+, and chromium 3+ ions using sodium hydroxide and ammonia. Now let's take a look at the aims of this experiment. Aims are listed down here. The first one is to identify the presence of nickel, ferrous, ferric, copper, and chromium 3+ ions in aqueous medium. So we will have these ions in separate aqueous mediums, and we are going to observe their colors, and we are going to carry out different tests to separately identify different types of complexes they are forming when reacted with sodium hydroxide, ammonia, and hydrogen sulfide in acidic and alkaline mediums. And the second objective is to explain different identification tests using differences in solubility of compounds. So as we react these ions with different chemical reagents, they will form different compounds, and these compounds will have different solubilities. So we are going to be using these differences in their solubilities to identify these ions as well. And the third one is to identify the complex formation by certain cations and to identify the colors of D block element cations. As you have already learned, D block element cations, transition metal cations, most of the transition metal cations have very characteristic colors in aqueous medium. And we are going to use that also to identify the presence of each of these cations in an aqueous medium, as well as the colors of different compounds they form as mentioned above. Now, let's move on to the next slide. In this slide, we are taught the same things that we heard about in the previous slide. So they are bringing up the solubility of hydroxides. So the very first thing we do is we take each of these aqueous cations and then we react them with sodium hydroxide and dilute ammonia. Both of these reactions most of the time produce metal hydroxides. So each of these cations produce metal hydroxides that are not soluble in water. So therefore, they are going to have precipitates formed, and these precipitates are going to be different in color. Then we will be adding ammonia or excess ammonia and excess sodium hydroxide to see if there are any reactions taking place in the presence of excess sodium hydroxide or excess ammonia. So we are going to learn about complex formation in the presence of excess ammonia or excess sodium hydroxide here as well. And then you'll be taking some of the metal hydroxide precipitate and we'll be heating it to observe if there are any color changes as we do that. So all of these will provide information about the identity of the cation that is present in an aqueous medium. As mentioned earlier, we'll be taking a look at the different types of complexes each of these metals will form with excess ammonia as well. Some of the metals will first form a hydroxide, and those hydroxides will dissolve in excess ammonia due to formation of a complex with ammonia. Because of that, we will be able to observe a very specific color when a complex is formed with different metal cations and ammonia ligands. So we are going to use this information to specifically identify different types of metal cations. Now, let's take a look at the reagents we need for this practical. So this is a list of equipment and the reagents we'll be using throughout this practical. We'll be using test tubes, glass rods, Bunsen burners for heating, and then we have chemicals. We will obviously need all of the metal cation aqueous solution. So we have listed them down here. And we are going to be taking them in 0.1 moles per decimeter concentration. We are going to be using dilute sulfuric acid, sodium hydroxide solution, ammonium hydroxide solution, and potassium ferricyanide and potassium ferrocyanide will also be used. We will be using both potassium ferricyanide and this is potassium ferrocyanide. We will be using both of those. We will be using potassium thiocyanate for this practical, or ammonium thiocyanate. Both of them can be used. We will be using hydrogen peroxide, and DMG, dimethyl glyoxime, will also be used in this practical. Now, without further delay, we will be taking a look at the very first cation we will be learning about, which is copper 2+ cations. So, copper 2+ identification tests. The very first test we will be doing when it comes to all of the cations is to react these cations with sodium hydroxide. As they react with sodium hydroxide, these cations will form its hydroxide. Copper 2+ when reacted with sodium hydroxide will form copper hydroxide. So a rough equation is given here. You can see when copper 2+ aqueous ions are reacted with sodium hydroxide, it is forming copper hydroxide solid, which is a water insoluble light blue color or pale blue color precipitate. By now, you should all be aware of the color of copper 2+ aqueous solutions. Copper 2+ aqueous solutions are pale blue in color, and when you react this pale blue color solution with sodium hydroxide, it forms a pale blue color precipitate. The equation for it is given here. Copper sulfate is what we normally obtain copper 2+ ions from. So we take copper sulfate, and when we react it with sodium hydroxide, we'll be forming copper hydroxide and sodium sulfate, which is going to be colorless. So you can see the supernatant above, the precipitate is colorless because sodium sulfate aqueous solutions do not have a color. And what you see here as a light blue color precipitate is your copper hydroxide. So that test will give us an idea. For example, if you ever take aqueous solution and if they mention that there is a transition metal cation there, you can identify it with few things. First of all, you can take a look at the color of the aqueous solution. If it is pale blue in color, you kind of get an idea that it could be copper 2+. And then you can confirm it by adding a little bit of sodium hydroxide. So when you do that, it will form a light blue color precipitate. So it gives the indication that this is copper 2+ ions. And if you want to take a step further and confirm definitively it is definitely copper 2+, you can move on to the next step, which is taking ammonia and reacting the solution with it. So first, if you take a little bit of that solution and react with dilute ammonia, you will be forming light blue color precipitate. But in this case, what is different to sodium hydroxide is if you take this light blue color copper hydroxide precipitate and react it with further ammonia or excess ammonia, this precipitate will dissolve to form a dark blue color solution. So that will tell us that this solution definitely contains copper 2+ ions. So take a look at this experiment. You can see when you take copper 2+ ions, and react it with dilute ammonia, we have formed a light blue color precipitate. And this light blue color precipitate, if you take it and if you react it with concentrated or excess ammonia, then this pale blue color precipitate will dissolve to form a dark blue color solution. So that point is mentioned here as the second point. When this reaction is carried out, the pale blue color precipitate dissolves to form a dark blue color solution. So you're going to form a dark blue color solution. Very important to keep in mind. As you can see here, when you take your copper hydroxide solid or copper hydroxide pale blue color precipitate and react it with ammonia, it forms a copper ammonia complex, tetra amino copper 2 ions. So as copper forms a complex with ammonia ligands, actually there will be 4 ammonia ligands connecting with the copper 2 plus ion, it will form a complex. The formula of the complex is given here, and that complex will be dark blue in color. So as you can see, the precipitate will dissolve to form a dark blue color solution. So you will be observing this in the lab. The blue color that is formed is a brilliant dark blue color. You will find it very appealing. So it is a beautiful reaction to observe in the lab as well. So we come to a little bit of a summary here when it comes to the reactions revolving around copper hydroxide. Copper hydroxide, when you react it with excess sodium hydroxide, will show no reaction. Copper hydroxide will not dissolve in the presence of excess sodium hydroxide. However, it will dissolve in excess ammonia due to copper 2 plus ion forming a complex with ammonia. So with 4 ammonia ligands, copper 2 plus ions will form a complex which is dark blue in color. So therefore, this copper hydroxide solid will dissolve in excess ammonia. You have to very clearly remember this. This test can be used to separately identify copper 2 plus ions from other types of ions. Since copper hydroxide is not soluble in sodium hydroxide, it is not an amphoteric hydroxide. If metal hydroxides react with bases, as you know, metal hydroxides will obviously react with acids. However, if metal hydroxides react with bases as well, those type of hydroxides are known as amphoteric hydroxides. So amphoteric hydroxides have the ability to react both with acids and bases. Over here, you can see that the copper hydroxide does not react with sodium hydroxide, which is a base, indicating that copper hydroxide is not an amphoteric hydroxide. Now we move on to the third test, reaction with potassium ferrocyanide. Potassium ferrocyanide. So potassium ferrocyanide formula is given here. Cyanide ligand is carrying 1 minus charge. So there are 6 cyanide ligands, indicating that they bring about 6 minus charges, and this is ferrous. So therefore, when they are forming a complex ion with ferrous, the overall charge of that complex ion should be minus 6 plus 2 added together. The overall charge would be minus 4. Sorry, the overall charge should be minus 4. This brings in plus 2. This brings in minus 6. So the overall charge is going to be minus 4 when you add them together. So that is why we have a plus 4 charge brought about by potassium ions. There are 4 potassium ions bringing in plus 4 charges. Now, that's just a little bit of a detail about potassium ferrocyanide. With that in mind, let's move on to the reaction that is taking place here. So if you take copper 2 plus ion solutions, over here we obtain copper 2 plus by dissolving copper sulfate in water. If you react the copper 2 plus aqueous solutions with potassium ferrocyanide, you will be forming copper ferrocyanide, which is going to be a precipitate which is chocolate brown in color. You can see in the image also, it is a chocolate brown color precipitate that we have formed here. which is due to copper 2 plus ions reacting with potassium ferrocyanide. This is a very specific identification test that you can do to identify copper 2 plus ions. The summary of all of the identification tests that we learned about is given here. You can take copper 2 plus ion solutions. As copper 2 plus ions are present in aqueous medium, it will form a complex with 6 water ligands. So whenever you dissolve copper sulfate in water will dissociate into copper 2 plus and sulfate ions. And these copper 2 plus ions will be surrounded with 6 water molecules to form hexaaqua copper 2 complex ion. This complex ion will have this pale blue color. And then you have the reactions that we carried out to identify the presence of copper 2 plus ions. When we added sodium hydroxide, we saw formation of copper hydroxide, which is a light blue color precipitate. And then we have added dilute ammonia. Upon addition of dilute ammonia, we saw the same observation of forming copper hydroxide, which is the light blue precipitate. However, if you add excess ammonia, we saw this light blue precipitate dissolves to form a complex tetraamine copper 2 ion. So this complex is dark blue in color. Afterwards, as a very specific identification test, we took potassium ferrocyanide and reacted with copper 2 plus ions, which formed a chocolate brown color precipitate due to forming copper ferrocyanide, which is a chocolate brown color precipitate. So this summarizes the identification tests we learned for copper. In the previous few tests, we learned what happens when you take an aqueous solution of copper 2 plus ions and then we react it with different reagents. In this particular test, what we do is we separate the copper hydroxide precipitate that was formed by addition of sodium hydroxide or dilute ammonium hydroxide, and then we heat it. Upon heating copper hydroxide pale blue color precipitate, we are going to observe that this pale blue color precipitate is going to turn to a black color precipitate. This black color precipitate is formed because copper hydroxide turns into copper oxide. Copper oxide, CuO. Copper oxide, CuO, is a black color solid. So if you take your copper hydroxide precipitate and if you heat it, you're going to observe a color change from light blue or pale blue to black. Another way that you can identify the presence of copper 2 plus ions in aqueous solution is by taking hydrogen sulfide in acidic medium and reacting it with copper 2 plus ions. As you know, copper 2 plus ions are categorized into group 2 of qualitative analysis. In group 2 of qualitative analysis, we know they form sulfides. So copper 2 plus ions are capable of forming sulfides even with a very low concentration of sulfide ions. So to bring about a very low concentration of sulfide ions, we actually have hydrogen sulfide in acidified medium or acidic medium. So at that point, hydrogen sulfide dissociation will be very low, releasing only a little bit of sulfide ions. We have spoken about this many times in our previous experiments. So when you have a very low sulfide concentration, at that point, you can see copper 2 plus can precipitate. Of course, even if you have really high concentrations of sulfide ions, at that point, copper 2 plus will very easily precipitate. But at the same time, there will be other metals that are capable of precipitating out at high concentrations of sulfide. To make sure that doesn't happen, we have to produce only a very low concentration of sulfide ions. So we use an acidified medium. So H2S in acidified medium or acidic medium, if you react it with copper 2 plus ions, you will be forming copper sulfide. And copper sulfide is going to be a black color precipitate. So if you observe a pale blue color solution turning into a black color precipitate in the presence of acidified hydrogen sulfide, that indicates the presence of copper 2 plus ions. With that, we now move on to nickel 2 plus ions. We looked at copper 2 plus, we discussed 5 different tests to identify copper 2 plus, and now we are moving on to nickel 2 plus. So as I mentioned earlier, we start all of our testing methods by adding sodium hydroxide because we are planning on forming the metal hydroxide first. So nickel is reacted with sodium hydroxide and it will produce nickel hydroxide solid. So the nickel hydroxide solid or nickel hydroxide is a water insoluble precipitate. So this water insoluble nickel hydroxide happens to be green in color. Nickel 2 plus ion solutions also happen to be green in color. So nickel 2 plus ion solution will appear green, but when you react it with sodium hydroxide, you're going to observe a green color precipitate formed. As you can see, the color of the solution is now gone as the solution had a green color due to the presence of nickel 2 plus ions. But now all of the nickel 2 plus ions are in this precipitate. Therefore, you can see the supernatant or the solution now is not having a green color. However, the precipitate is going to be green in color. So the reaction for this, the balanced chemical equation is given here. Nickel chloride, when reacted with sodium hydroxide, forms nickel sulfide along with sodium chloride. Same observation, only that we have given here the balanced chemical equation. If you take your nickel hydroxide solid, which is a precipitate, if you take this precipitate and then react our nickel hydroxide precipitate with excess sodium hydroxide, what you will observe is there is no further reaction taking place. Because when it comes to nickel hydroxide is not an amphoteric hydroxide. We learned about amphoteric hydroxide a little while ago. If you have a hydroxide, a metal hydroxide that is capable of reacting with both acids and a base, those are referred to as amphoteric hydroxides. However, this indicates when you add excess sodium hydroxide and if the precipitate that is formed does not dissolve, this indicates that this precipitate or nickel hydroxide is not an amphoteric hydroxide. So, first observation, it does not dissolve in the presence of excess sodium hydroxide. And the second observation based on that, or inference based on that, is nickel hydroxide is not an amphoteric hydroxide. Let's move on to the second test. Reacting nickel 2 plus aqueous solution with ammonia. So as you can see, our nickel 2 plus aqueous solutions are green in color. You can see it very clearly here. And as you react it with ammonium hydroxide or dilute ammonia, we are going to see the formation of that green color precipitate we saw earlier as well. So nickel hydroxide precipitate can be formed both with ammonia and sodium hydroxide. So this green color precipitate that you have is your nickel hydroxide. And then if you take this nickel hydroxide precipitate and then react this nickel hydroxide precipitate with excess ammonia or concentrated ammonia, then what happens is you will see that this green color precipitate dissolves to form a blue color solution. Again, this is due to the nickel 2 plus ions being able to form a complex with ammonia ligands. So in the presence of excess ammonia, the nickel hydroxide precipitate will dissolve to form a blue color solution. So this blue color solution is a result of this nickel ammonium or ammonia complex. So hexaamine and nickel 2 ions. So hexaamine nickel 2 ions are going to have this blue color or characteristic blue color in its solution. So this observation is also very important. As we saw earlier, nickel 2 plus ions, when forming a hydroxide with sodium hydroxide or dilute ammonia, it was a green color precipitate. And this green color precipitate did not react with excess sodium hydroxide. However, it does react with excess ammonia and dissolve in excess ammonia to form a blue color solution, which is due to the formation of nickel ammonia complex. So this is the observation that you should keep in mind, and based on this we should take note of two things. Nickel hydroxide is not an amphoteric hydroxide, and nickel is capable of forming a complex with ammonia ligands, and that complex happens to be dark blue in color. Now we move on to our third test revolving around nickel. If you take nickel 2 plus aqueous ion solution and react with dimethylglyoxime or DMG, commonly referred to as DMG, this test is a very specific test because when you take DMG, dimethylglyoxime, and react with nickel 2 plus ion, you get a very nice cherry red precipitate or red color precipitate. So very interesting observation when you are carrying this out in the lab. So you will see when you react DMG, dimethylglyoxime, with nickel 2 plus ion solution. Now nickel 2 plus ion solution is what? Green in color. And as you add DMG, it will form a red color precipitate. So this specific test can be used to identify nickel 2 plus ions, and this will answer only to nickel 2 plus ions. So therefore, this test can be used to identify a solution containing nickel 2 plus ions. So some of our observations are summarized here. If you take nickel 2 plus ions, we can take nickel 2 plus ions into a medium, and when you have nickel 2 plus ions in aqueous medium, they form hexa aqua nickel 2 complex, hexa aqua nickel 2 complex, or hexa aqua nickel 2 ions. So those ions are going to be green in color. So the solution appears green, and if you add sodium hydroxide, the solution will produce a blue. And if you add sodium hydroxide, that solution will produce a green color precipitate. If you add dilute ammonia, you will see the same green color precipitate being formed, which is nickel hydroxide, which is not soluble in water. And if you add excess concentrated ammonia, you will see it will form a dark blue color solution. This is due to nickel 2 plus ions forming a complex with ammonia ligands. And finally, we added DMG, dimethylglyoxime, to nickel 2 plus ions to observe the formation of a red color precipitate. Let's move on to the fourth test. Now, nickel 2 plus ions are found in the fourth group of qualitative analysis. Now, fourth group includes ions that will form a precipitate with a high concentration of sulfide ions. So all of the metal ions in the fourth group of cation analysis, you will see them forming sulfides with high concentrations of sulfide ions. So to obtain a high concentration of sulfide ions, we normally introduce hydrogen sulfide in an alkaline medium. So we have to take ammonia. So when you have ammonia or H2S in alkaline medium, H2S will dissociate quite a lot and will produce a lot of sulfide ions. This will produce a higher concentration of sulfide ions, and in the presence of a higher concentration of sulfide ions, Nickel-2+ ions will precipitate. However, Nickel-2+ will not precipitate in a low concentration of sulfide ions. So therefore, Nickel-2+ is not found in the group 2. Copper-2+ is found in the group 2. So that's why when it comes to precipitating out copper-2+ ions, we used H2S in acidified medium or acidic medium. At that point, sulfide ion concentration in acidic medium would be very low. But when you have hydrogen sulfide in alkaline medium, due to hydrogen sulfide dissociating more, you will have more sulfide ion concentration, allowing the precipitation of nickel sulfide, as nickel sulfide will only form a precipitate in high concentrations of sulfide ions. As you can see here, when you react Nickel-2+ ions in alkaline hydrogen sulfide or hydrogen sulfide in alkaline medium, you will form nickel sulfide here along with H+, and you can see a green color solution has now turned into a black color nickel sulfide precipitate. Another test that you can carry out is if you take your nickel hydroxide, the green color precipitate that you obtained, and if you heat it, it will turn into a little bit of a darker green color. It will not turn black. However, it will be also a green color precipitate, but this precipitate is not nickel hydroxide. This precipitate is nickel oxide. Sometimes you will not be able to distinguish between the two colors. However, as you heat nickel hydroxide, you have to keep in mind that it turns into nickel oxide. So the reaction revolving around that is given here. When you heat nickel hydroxide, it releases water and turns into nickel oxide. Now we move on to ferric, Fe3+ ions. When it comes to Fe3+ ions, aqueous solutions of ferric ions happens to be yellow-brown in color. Aqueous solutions of Fe3+ happens to be yellow-brown in color. You can observe the color here. Now students, you have to keep in mind a very important point. That is, when it comes to different types of metal ion complexes and their colors might vary depending on a few factors. One of the factors that we have to keep in mind is the concentration. If you have a high concentration of the metal ion that you are looking into, sometimes the color observed will not be your textbook definition of yellow-brown. Sometimes it might appear a little bit more intense than this specific color. So if you have a very low concentration of Fe3+ ions in the medium, again, you might not even observe a color. So keep in mind the concentration of the ion complex that you're looking at is playing a major role in giving off the color that you observe. So that is something that you should keep in mind at all times. So Fe3+ ions, if you have a moderate concentration or good enough concentration of Fe3+ ions in an aqueous medium, it will appear yellow-brown. And when you add sodium hydroxide to it, Fe3+ ions will form ferric hydroxide, ferric hydroxide will be a red-brown precipitate. So this is FeOH3 or FeOH thrice, and you can see the precipitate that is formed is a red-brown precipitate. However, these precipitates do not react with excess sodium hydroxide. If you add excess sodium hydroxide to ferric hydroxide precipitate, it will not show any reaction. So therefore, ferric hydroxide is not amphoteric. What about the reaction with ammonia? So if you take ferric or Fe3 plus aqueous ion solutions, and if you react it with ammonium hydroxide, you will form the same red-brown precipitate first. So due to the formation of water-insoluble ferric hydroxide. So ferric hydroxide is red-brown precipitate, and you will observe it even when you're adding dilute ammonia. Now, up until this point, whenever we formed a hydroxide, we saw if you added excess ammonia, that precipitate dissolved. However, you will not make that observation here with ferric. If you add excess ammonia, the precipitate formed, ferric hydroxide, will not dissolve. This is due to ferric ions not forming a complex with ammonia ligands. So therefore, with excess ammonia or excess ammonium hydroxide, you will not be seeing the formation of a different complex. You will not be seeing the precipitate dissolving in the presence of excess ammonia. Now we are moving on to the third step here. Adding potassium ferricyanide to an aqueous solution of Fe3 plus ions. Potassium ferricyanide. So when you take potassium ferricyanide, as mentioned here, so what you have here is our potassium ferricyanide, and we have our Fe3 plus ions here. So if you react potassium ferricyanide with Fe3 plus ions, you will see the formation of a brown color solution. Ferricyanide will be formed, and the color is going to be brown. So this is the observation when you add potassium ferricyanide to an aqueous solution of Fe3 plus ions. That is something that you should keep in mind. And now we move on to the fourth step, where this is a very interesting part of this experiment. I hope that you also get to do this in the lab. So if you add potassium iodide into an aqueous solution of Fe3 plus ions, then what happens is Fe3 plus ions get reduced to form Fe2 plus ions. So ferric ions turn into ferrous ions. Yellow-brown ions turn into pale green color ions. Now ferrous ions are pale green in color, but as I mentioned earlier, it all comes down to the concentration sometimes. And then iodide ions turn into iodine. So this is an oxidation from 1 minus to 0. So iodide ions, when turning into iodine, as you know, iodide ions do not necessarily give off a color. However, iodine in aqueous medium appear brown. So due to the presence of iodine in water, the solution will appear brown. The pale green color will be masked by the brown color of iodine. So the resultant solution is going to appear brown. So a yellowish brown solution turns into brown. Now, how do we actually get to observe the presence of iodine here, that this reaction actually happened? We can confirm the taking place of this reaction by adding carbon tetrachloride, which is an organic solvent, which is nonpolar. So iodine is nonpolar. Now, as you observe in this diagram that we have here, at the bottom what you have is your aqueous iodine solution, I2 in aqueous medium. So it is appearing brown. And as you add CCl4, carbon tetrachloride, which is a non-polar solvent, it is heavier than water as well. So you will see carbon tetrachloride will sink to the bottom of this test tube and water will be floating on top of carbon tetrachloride. Water will be lighter, less denser than CCl4. So water layer will be on top and the CCl4 layer will be on the bottom. So as you add it, the color of CCl4 will not necessarily change. But after you add it, if you stir it really well, if you mix it really well, then what happens is the iodine in the water actually comes into the carbon tetrachloride layer, or which is the nonpolar layer. So this is due to the fact that iodine is nonpolar and CCl4 is also nonpolar. You might have heard of the phrase, likes dissolves like. So likes dissolve likes. So basically iodine is nonpolar. It loves to get dissolved in a nonpolar layer, which is CCl4. So therefore iodine will move from the aqueous layer into the nonpolar CCl4 layer. So CCl4 layer, carbon tetrachloride layer, actually turns purple. So in nonpolar solvent, iodine appears to be purple in color. So aqueous layer will lose the brown color that it had. It will be slightly brownish still, because not all of the iodine will move completely into the CCl4 layer, but majority of the iodine will move into the carbon tetrachloride layer. So there's going to be a slight hue of brown in the aqueous layer still. So this confirms that iodide ions did get converted into iodine. This is due to ferrous ions can be formed. This is due to the fact that ferric can be converted into ferrous in the presence of iodide ions. So this test is also a test that you can carry out to identify the presence of Fe3 plus ions. Finally, we have adding potassium thiocyanate or KSCN to an aqueous solution of Fe3 plus ions. So if you take potassium thiocyanate, what we're trying to introduce here is the thiocyanate ion, so you can take ammonium thiocyanate as well. So in the presence of the thiocyanate ion, ferric ions will form this complex. So this complex that is formed here, ferric thiocyanate complex, is going to be a red color aqueous solution. So you will see the yellow-brown solution turns into a red color solution. So this observation again confirms the presence of Fe3 plus ions in this yellow-brown aqueous medium. So now let's move on to identification test for ferrous, Fe2 plus. So as you can see here, like all other experiments, we are starting with the same reaction. We are taking Fe2 plus ions. So Fe2 plus ion solutions are light green in color or pale green in color when they are in aqueous medium. And then we are going to react these aqueous ion solutions with sodium hydroxide. So as you react ferrous ions with sodium hydroxide, they will form ferrous hydroxide solid. Ferrous ions and sodium hydroxide will result in ferrous hydroxide. So ferrous hydroxide is a water insoluble solid which appears a dark green. So this green color is normally characterized as a dirty green color. So we say ferrous hydroxide solid is dirty green in color. And at the same time, if you add excess sodium hydroxide to this, so ferrous hydroxide solid is isolated and we add excess sodium hydroxide to it, you will observe no reaction. You will not see ferrous hydroxide dissolving to form some sort of a solution. So this is due to the fact that by now you should know what we are leading up to. So if a metal hydroxide does not dissolve in sodium hydroxide or any base, that means that metal hydroxide was not an amphoteric hydroxide. So first observation, ferrous hydroxide does not dissolve in sodium hydroxide, and the inference is it is not an amphoteric hydroxide. Now let's move on to our next slide. Add dilute ammonia to an aqueous solution of ferrous ions. So dilute ammonia. When you add dilute ammonia to ferrous ions, we see the same observation as when we added sodium hydroxide. We form ferrous hydroxide. Ferrous hydroxide is a water-insoluble, dark green or dirty green color precipitate. So it's the same precipitate here. Now we have written here dark green, but keep in mind the characteristic name that is given for this particular precipitate is dirty green color precipitate. So the reaction is given here, and if you take excess ammonia, excess concentrated ammonia or excess ammonia, you will see that there is no reaction taking place. Before we come to ferric or ferrous solutions, we saw all the other ions that we looked at in this particular experiment. For example, copper 2+ and nickel 2+. They both reacted with excess ammonia and dissolved their hydroxide, metal hydroxide, to form different types of complexes. So copper formed a blue color precipitate, copper hydroxide, but when added with excess ammonia, this copper hydroxide precipitate dissolved to form a dark blue color solution. Nickel also formed a precipitate when reacted with hydroxide, nickel hydroxide, which is a green color precipitate, and when reacted with excess ammonia, it also formed a blue color solution. So as you can see, both copper and nickel did dissolve their hydroxide in excess ammonia, but ferrous and ferric does not dissolve their hydroxide in excess ammonia, nor does it dissolve the hydroxide in excess sodium hydroxide. Now let's move on to the next test. Adding potassium ferricyanide to an aqueous solution of Fe2+ ions. The reason why we refer to this as potassium ferricyanide is because in this complex what we have is a ferric ion. So cyanide groups are forming coordinate bonds with a ferric ion and forming the ferricyanide ion. And when you react potassium ferricyanide, this ferricyanide ion will come into the medium, and if you add Fe2+ aqueous ions into potassium ferricyanide, or if you add potassium ferricyanide into Fe2+ aqueous ions, you'll be forming a Prussian blue color precipitate. So it's a deep blue color or a Prussian blue color precipitate will be formed. Initially, when you add potassium ferricyanide to our pale green color Fe2+ aqueous solution, what you will observe is a blue coloration in the aqueous medium. You will observe that the entire medium appears blue. You might even think that this blue color that you see in the aqueous medium is due to formation of a blue color solution. However, what you form here is not a solution, it is in fact a precipitate. But this precipitate will be formed in such small particle size. Due to that, these particles, when dispersed in aqueous medium, will make the aqueous solution appear blue. However, if you let it stand for a while, you will see the blue color precipitate particles will collect at the bottom, and you will be very clearly observing the blue color of the precipitate. So students, one important observation is the formation of the Prussian blue color precipitate. And one very important point to keep in mind is as you add potassium ferricyanide to Fe2 plus ion solutions, the solution appears blue, maybe even tricking you to believe that you have formed a blue color solution. But keep in mind, it is not a solution that is formed. Instead, what you are observing is the precipitate particles that are really small, dispersed throughout the aqueous medium, giving you the illusion of forming a solution. However, in reality, what you have formed is a precipitate, which is Prussian blue or dark blue in color. You can observe this precipitate collecting at the bottom of the test tube or any container that you're carrying out the experiment in. If you allow the test tube to stand for a while, you will see the precipitate particles collecting at the bottom. Now, adding potassium ferrocyanide. So what you have over here is a ferrous ion to an aqueous solution of Fe2 plus ions. In this particular reaction, the pale green color Fe2 plus aqueous ion solution, when reacting with potassium ferrocyanide, it will form this precipitate or this complex, which happens to be a white color precipitate. So when you react Fe2 plus ions with potassium ferrocyanide, we are going to be forming a white color precipitate. The formula of the white color precipitate is given above. If you remember, we carried out an experiment where we took a little bit of Fe3 plus ion solution and we reacted the ferric ion solution with potassium thiocyanate. So as you react potassium thiocyanate with Fe3 plus ions, what was the observation? We saw the yellow-brown Fe3 plus ion solution turning into a red color ion solution, or we can say the yellow-brown solution turned red. So what is the reason for that? We saw that potassium thiocyanate, when in aqueous medium, dissociates into potassium ions and the thiocyanate ions, and thiocyanate ions are capable of forming a complex ion with Fe3 plus, which happens to be red in color. So therefore, the yellow-brown aqueous medium turned to a red color solution. Would we observe the same with Fe2 plus? Let's have a look. We see if you add potassium thiocyanate to an aqueous solution of Fe2 plus ions, no color change will be observed. So no color change. When heated with nitric acid, red color will be formed. So this sentence, we have to understand. First observation is there is no color change. However, if you react the Fe2 plus aqueous ion solution with nitric acid and then add potassium thiocyanate, you will see the red color being formed. So this is due to, students, when it comes to adding potassium thiocyanate to Fe2 plus, there's no reaction. You don't see a color change, no reaction at all. However, now you can see when you add potassium thiocyanate in both situations, you only see a green color solution, as Fe2 plus ions will not be changing its color. However, in the presence of nitric acid, Fe2 plus ions get oxidized to form Fe3 plus ions. So if you take Fe2 plus ion solution and add nitric acid and then you heat it along with potassium thiocyanate, then you will see the red color being formed. But if you just add potassium thiocyanate to Fe2 plus ion solution, nothing will happen, because with ferrous ions, thiocyanate ions will not form a red color solution. However, if you had nitric acid in the mix and if you heat the solution, it will speed up the oxidation of Fe2 plus to Fe3 plus. And as Fe3 plus gets formed, potassium thiocyanate will react with Fe3 plus and will form a red color solution. So this reaction is given for this balanced chemical equation, is basically giving us the reaction between nitric acid and ferrous ions. So in the presence of nitric acid, ferrous ions turn into ferric ions. So the pale green color solution turns to a red-brown solution. This indicates Fe2 plus was converted to Fe3 plus. And then if you added potassium thiocyanate, at that point we know very well Fe3 plus will turn into, or the yellow-brown solution of Fe3 plus ions will react with the potassium thiocyanate to form a red color solution due to Fe3 plus ions forming a complex ion with thiocyanate ions. So we have a red color solution formed. If you take ferrous ions and then react it with nitric acid and heat it, then you form ferric ions. And at that point, if you add potassium thiocyanate, it will react to form a red color solution. With that, we move on to chromium 3 plus ions. Chromium is also a very interesting ion. As you know, many of the students by now have learned about different types of oxidation states of chromium and the colors involved, as well as you might have even conducted redox titrations with the use of chromium compounds, or such as chromate and dichromate ions. Now we are going to look at chromium 3 plus ion chemistry, or how to identify the presence of chromium 3 plus ions in aqueous medium. As always, we are going to be adding sodium hydroxide to begin with this test. So if you take a chromium 3 plus aqueous ion solution, it will appear green. Chromium 3 plus aqueous ion solution will appear green in color. And if you add sodium hydroxide, chromium 3 plus will react with the hydroxide ions to form chromium hydroxide, which is a green color precipitate. Green color solution forms a green color precipitate. Can you think of another green color solution forming a green color precipitate in the presence of sodium hydroxide? If you thought of nickel, you'll be correct, because nickel 2 plus ions are also green in an aqueous medium. And if you react with sodium hydroxide, it will also produce a green color precipitate. So chromium and nickel both will produce a green color precipitate. Apart from that, you can also bring in ferrous ions into the picture. However, ferrous ion aqueous medium or Fe2 plus aqueous ion medium will be pale green in color, so somewhat lower in color intensity, and the precipitate formed was a little bit more identifiable because it was dirty green in color. When you react Fe2 plus with hydroxide ions, we formed a dirty green color precipitate. So we know of 3 green color solutions forming 3 green color precipitates. When excess sodium hydroxide is added to the precipitate, it dissolves to form a green color solution. So all the other 2 green color precipitates of nickel hydroxide and ferrous hydroxide did not react with excess sodium hydroxide. However, chromium hydroxide does. So chromium hydroxide, when added with excess sodium hydroxide, will dissolve to form a green color solution. So chromium hydroxide, which is a precipitate, green color precipitate, will dissolve in the presence of excess sodium hydroxide. So this is a very important observation because we have 3 different green color solutions producing green color hydroxides. However, there's only one green color hydroxide that will dissolve in excess sodium hydroxide. So in excess sodium hydroxide, we saw chromium will form a complex with hydroxide ions, and that complex is going to be a green color solution. So the reaction for that or equation for that particular reaction is given here. So what does this mean? Now observation is, the first thing to do is observe what is taking place. If you take the chromium hydroxide green color precipitate, if you react it with sodium hydroxide, the observation would be the hydroxide dissolves to form a green color solution. What is the inference? Inference would be chromium hydroxide is an amphoteric hydroxide. Chromium hydroxide is an amphoteric hydroxide. Now let's move on to the next slide. Reacting aqueous solution of chromium with sodium hydroxide and hydrogen peroxide. Now the reason why we do it here itself is that we have already taken chromium hydroxide and dissolved in even more sodium hydroxide. So we have this chromium complex with us, or chromium ions in an alkaline medium is already obtained. At this point, it is easier for us to convert chromium into chromate ions because this conversion requires an alkaline medium. So after we obtain chromium in an alkaline medium, or chromium ions in an alkaline medium, all that you have to do is addition of hydrogen peroxide. So if you add hydrogen peroxide to chromium ions in an alkaline medium, you will form chromate ions. I'm quite sure you are very familiar with chromate ions. Chromate ions are yellow in color. So you can form chromate ions by taking chromium 3 plus ions in alkaline medium, or you can first of all take chromium 3 plus ions, add a little bit of sodium hydroxide to form a precipitate. If you add even more sodium hydroxide, the precipitate will dissolve to form a green color solution like this. And to that particular solution, if you add hydrogen peroxide, you will form a yellow color solution, which is your chromate ion, CrO4 2 minus. So the equation for that reaction is given here. The full chemical equation for that reaction is given here. 2 chromium 3 plus ions and 3 hydrogen peroxide and 10 hydroxide ions will form 2 chromate and 8 water molecules. And the solution will be yellow in color. So the next step is to understand what type of oxidation changes are taking place here. When chromium 3 plus ions or chromium hydroxide is reacted with sodium hydroxide and hydrogen peroxide, we know the yellow color solution containing chromate ions will be formed. So now we have to understand which chemical species is actually undergoing oxidation and which chemical species is undergoing reduction. If you take chromium complex, we know the green color solution that forms in the presence of excess sodium hydroxide is this particular complex that we have over here. We have 4 hydroxide ions connected to 1 chromium cation, and the oxidation number of chromium is +3. In hydrogen peroxide, the oxidation number of oxygen happens to be 1-. So as you can see, when you take a look at chromium in both reactant and product, in the product, the chromium is present in the oxidation number +6 and oxygen will be in -2 oxidation state. So chromium has gone from +3 to +6, which is an increase in oxidation number, so it is an oxidation. And if you take a look at oxygen, it has gone from -1 to -2, so it is a decrease in oxidation number, which indicates it has undergone a reduction. So hydrogen peroxide or oxygen in hydrogen peroxide has reduced while oxidizing our chromium from chromium 3 plus to the oxidation state +6 in the chromate ion. Now let's move on to the next slide. Now students, in this slide, it summarizes how you can actually make your chromate ion starting from chromium 3 plus aqueous solutions, chromium hydroxide, the green color precipitate, or the green color solution formed when dissolving the green color precipitate in excess sodium hydroxide. So you can start from any of these points, because either way, even if you start with chromium 3 plus, you have to add sodium hydroxide to make the medium alkaline. So at this point you are forming chromium hydroxide, but in the addition of excess sodium hydroxide, you are anyway going to be forming the complex of chromium and hydroxides. So therefore, you can start with either of these places, and after adding more hydroxide or sodium hydroxide and hydrogen peroxide, you are going to obtain your chromate ion, CrO4 2- chromate ions, which is a yellow color solution. So chromate ion solutions happens to be yellow in color. Dichromate, on the other hand, is going to be orange in color. Now with that, let's move on to identification test for zinc 2 plus ions. Adding sodium hydroxide to an aqueous solution of zinc 2 plus ions. So as you know, we will always start our experiments with adding sodium hydroxide in this particular practical to different types of cations. So we have zinc 2 plus cations. Zinc 2 plus is not a transition metal cation. So I would like to remind you of that since we are talking about zinc 2 plus here. Zinc 2 plus is not considered to be a transition metal cation because zinc 2 plus does not form any stable ions containing incompletely filled d orbitals. So therefore, zinc 2 plus does not fall under transition metals. However, when you are reacting with sodium hydroxide, so before I move on to that, zinc 2 plus ion solutions, since they are not containing any incompletely filled d orbitals, they happen to be colorless. So if you take a zinc 2 plus aqueous ion solution and react it with sodium hydroxide, you will form a water insoluble metal hydroxide, zinc hydroxide. However, this is not going to have a color. This is going to be white in color. We don't have a very colorful color here like green or blue or red. We don't have different other colors like that. You can see we are just forming a white color precipitate. So now, if you remember correctly, the next step that we will be doing is adding excess sodium hydroxide to see if it dissolves. So let's move on to the next slide. So when the precipitate is added with excess sodium hydroxide, the precipitate dissolves to form a colorless solution. So this is the observation. We have the precipitate, a white color precipitate, and you can observe the white color precipitate here. If you react this precipitate with excess sodium hydroxide, you actually form a colorless solution. This indicates what you have here is an amphoteric hydroxide. So what you have here is an amphoteric hydroxide. So the equation for that reaction is given here. You can see how zinc hydroxide ends up forming a complex with excess hydroxide ions. So zinc hydroxide will form a colorless solution in the presence of excess sodium hydroxide. Now students, in this slide, let's take a look at what they ask us to do. They say when dilute HCl is added to a colorless solution obtained above, a white color precipitate will be formed again. So what is happening here? So we have another solution formed when we reacted the zinc hydroxide solid with excess sodium hydroxide. We obtained a colorless solution, and now we take that colorless solution and react it with HCl. So when you add HCl to this solution, the hydroxide ion concentration will go down due to reacting with HCl. So therefore, zinc can no longer have the zinc hydroxide complex, which will force zinc to go back into zinc hydroxide state, which is a white color precipitate. So this reaction is what is happening when it comes to adding dilute HCl. So dilute HCl will remove hydroxide from the medium, lowering the concentration of hydroxide ions, because in higher concentrations of hydroxide ions, zinc will form a complex which is colorless solution. And if you remove some hydroxide ions from the medium and lower the concentration of hydroxide ions, zinc will be forming the white precipitate, which is zinc hydroxide again. So you can form a colorless solution by adding more and more sodium hydroxide to zinc hydroxide precipitate. But if you want to observe the formation of the white color precipitate again, you can add a little bit of HCl. So we will take a look at this reaction in detail here. You can see zinc 2 plus ions in the aqueous medium is going to have this particular formula, hexa aqua zinc 2 complex ion. So this complex ion will react with sodium hydroxide to form zinc hydroxide, which is a water insoluble white color precipitate, which we have indicated here. However, in the presence of excess sodium hydroxide, we will be able to form a colorless solution, which is formed due to 4 hydroxide ligands forming coordinate bonds with a zinc 2 plus ions, tetrahydroxo zincate 2 ion. So this colorless complex can react with HCl to form dilute HCl. So if I go a step back, a common formula and a name given to the colorless solution that is formed when zinc hydroxide is dissolved in excess sodium hydroxide is sodium zincate. Na2ZnO2. So this particular complex or this formula is often referred to as sodium zincate, which is a colorless solution. This is formed when zinc hydroxide is reacted with excess sodium hydroxide. So you have the sodium zincate colorless solution here. If you react with HCl, you will again form your zinc hydroxide white color precipitate. And if you add excess sodium hydroxide, again you will form a colorless solution. In this case, the colorless solution is this. So this same formula can be written here as well. So the colorless solution that is found over there is the same as the colorless solution that we have over here. I can write it here, Na2 ZnOH 4 times. So the colorless solution that we have formed at the right hand corner of this diagram is the same as the colorless solution that we have formed over here. So we have two colorless solutions. One is this, the other one is this. These two colorless solutions are formed due to two different complex ions. So we have to keep that in mind. It's not the same complex that is forming these two colorless solutions. Now, let's move on to the next test that we do with zinc. If you take zinc 2+ ions, if you react it with dilute ammonia, a white precipitate is formed. Just like in the previous case, zinc will turn into zinc hydroxide in the presence of dilute ammonia. You can see the white color precipitate being formed here. When excess ammonia is added, when you have added additional or excess ammonia into this white color zinc hydroxide precipitate, that precipitate will dissolve to form a colorless solution. So zinc hydroxide does react with both sodium hydroxide and ammonia in excess and will form a colorless solution. But again, this colorless solution has a different formula. So as you can see here, this is the chemical equation. If you take zinc hydroxide and if you react it with ammonia, what you get is a colorless solution due to 4 ammonia ligands forming coordinate bonds or dative covalent bonds with zinc 2+ cation. Tetraamine zinc 2+ ions. So we can call this tetraamine zinc 2 ions. So this complex is also colorless. This complex is also colorless. As you have heard already, keep in mind, zinc hydroxide dissolves in excess sodium hydroxide to form sodium zincate. So what we know as sodium zincate is tetrahydroxo zincate 2 ion. So this complex is also going to be colorless, as well as when you are reacting zinc hydroxide with excess ammonia, we form tetraamine zinc 2 ions. So both of these ions, along with hexa aqua zinc 2+, are going to be colorless. Now, finally, we move on to heating solid zinc hydroxide. Now, zinc hydroxide precipitate that we obtained was white color, and we take this white color solid sample and we are going to heat it. While heating, the resultant solid oxide appears yellow. So, as you heat zinc hydroxide, it forms zinc oxide. But while you are heating it. While you're providing a lot of heat to this, if you are doing this in a crucible, if you are heating this using a crucible, while you provide heat to this crucible, the zinc oxide solid that is formed is going to appear yellow. However, after you allow it to cool down, you will observe that this zinc oxide solid is now turning white. So this is a good way of identifying zinc oxide. So as you heat it, zinc oxide appears yellow, and when you cool it to room temperature, zinc oxide will appear white again. So this diagram indicates that cycle, giving you the idea when you heat it, it is going to turn into a yellow color. When you are cooling it again back into the room temperature, the zinc oxide is going to appear white. Another observation another test rather we can do for zinc 2 plus ions is if you react zinc 2 plus with hydrogen sulfide in alkaline medium or in ammonia, you will see the formation of a white color precipitate. So zinc sulfide is going to be a white color precipitate. The zinc 2 plus is found in the group 4 of qualitative anion of cations. And as I mentioned earlier, at high concentrations of sulfide ions, zinc 2 plus will be forming a sulfide precipitate or zinc sulfide precipitate. This zinc sulfide precipitate is going to be white in color. So zinc is one of the easiest compounds to remember the colors of, because everything revolving around zinc is going to be colorless. Solutions are going to be colorless. White color precipitates are formed when you're reacting it with different types of reagents. So zinc sulfide here is also going to be a white color precipitate. Now students, we have come to an end in the theory parts revolving around experiment number 23. Let's move on to the lab and actually conduct these experiments and observe these reactions. GCE Advanced Level Chemistry Practical Series, experiment number 23. Identification of nickel 2 plus, ferrous, ferric ions or Fe2 plus, Fe3 plus ions, copper 2 plus and chromium 3 plus ions. In this practical, we aim to give you the necessary information to identify these said ions, as well as we will give you the information that you need to explain how these identification tests are carried out with the use of differences in their solubilities of the compounds they form, as well as we'll be looking into how we can differentiate these solutions by observing the complexes they form and the colors of the cations of the D block elements that we see here in this experiment. So let's move on to identifying the reagents we will be using to carry out this experiment. Let's take a look at the reagents we will be using for this experiment. We will be using DMG, or known as dimethyl glyoxime. We will be using hydrogen peroxide, H2O2. We will be using two forms of ammonia, one concentrated, the other solution would be a dilute ammonia solution, and we'll be using sodium hydroxide as well. Apart from that, we'll be testing out these ions, nickel 2 plus ions, Fe2 plus ions, Fe3 plus ions. Then we'll be testing out copper 2 plus ions and finally chromium 3 plus ions. What you see here are the aqueous solutions of those ions. We have here nickel 2 plus ion solution. You can see it's a green color solution. We have here Fe2 plus or ferrous ion solution, which is a very pale green color solution. And then we have Fe3 plus ion solution, which is going to be a yellow brown color ion solution. we have copper 2 plus ion solution, which is a pale blue color. And finally, we have our chromium 3 plus aqueous ion solution, which is a green color ion solution. Apart from these ion solutions, we will be using potassium ferricyanide and potassium ferrocyanide, and finally we will be using potassium thiocyanate solution. Apart from the reagents that I showed you just now, we will be needing additional boiling tubes to carry out this reaction, and we'll be using a few droppers as well as a wash bottle. So let's move on to our first experiment with copper 2 plus aqueous ion solution. Let's move on to our first practical or first experiment, where we will see nickel 2 plus ions being reacted with sodium hydroxide, ammonia and dimethyl glyoxide. So let's add a little bit of water into this boiling tube and dilute this ion solution a bit further. Now, after diluting the solution a bit further, let's take another boiling tube and transfer small amount of it into a different boiling tube. Actually, let's transfer equal quantities into 3 different boiling tubes. Now that we have separated it into 3 different boiling tubes, let's move on ahead and add sodium hydroxide. We'll take one boiling tube and we will add a little bit of sodium hydroxide to see what the observation would be. Students, what do you see here? You can see a formation of a green color precipitate. I have not yet shaken it. So upon addition of sodium hydroxide, you will see the formation of a green color precipitate. So if I shake it a little bit, you can see the green color precipitate gets dispersed throughout the media. But if we add a little bit more sodium hydroxide, let's see if we can increase the precipitate a little bit. Right. Now you can see the entire aqueous medium here is green in color due to the formation of a green color precipitate, which is nickel hydroxide, NaOH twice. Right. So what you see here is a fine particles of nickel hydroxide being dispersed through the aqueous media, making it look like a cloudy solution. But make no mistake, this is nickel hydroxide solid particles that is present here. So the precipitate is present when you add sodium hydroxide to a nickel 2 plus aqueous solution. So let's move on to the next step, where we add excess amount of sodium hydroxide to see if the nickel hydroxide we have here will dissolve in the excess sodium hydroxide. I will be adding more sodium hydroxide onto this. As you can see, upon addition of more sodium hydroxide, the precipitate did not dissolve. If I give it a little shake, if I swirl it around a little bit, you will see the precipitate does not dissolve to form a clear solution. Please note that observation. No matter how much I swirl it around, still the cloudiness of this aqueous medium, or actually the suspension of nickel hydroxide particles, will not dissolve.
right? So nickel hydroxide solid is still present in this medium. Now this is evidence that nickel hydroxide is not an amphoteric hydroxide, which means addition of sodium hydroxide or in the presence of excess amount of sodium hydroxide, the nickel hydroxide will not dissolve, indicating that it is not an amphoteric hydroxide. Let's move on to our next experiment. We'll take another sample of our nickel 2 plus aqueous solution, and we will add a little bit of dilute ammonia. Take a look at this observation. Like in the previous experiment that we did, when we added sodium hydroxide to nickel 2 plus aqueous solution, we saw the formation of nickel hydroxide. Over here as well, you can see the formation of a green color precipitate. What you see over here is also nickel hydroxide being formed in the presence of dilute ammonia. So what you have here is NaOH twice, nickel hydroxide, a green color precipitate. If I give it a little shake, you can see the green color precipitate gets dispersed throughout the media, forming a cloudy suspension. So to this, let's add excess amount of ammonia to see if it will dissolve in excess ammonia. So to do this, I'll be using concentrated ammonia solution, and let's observe what happens when I add concentrated ammonia into this nickel hydroxide suspension we have here. What we have here is concentrated ammonia. We'll add a little bit of it into the medium. You can see instantly when I added concentrated ammonia, the color of the solution started to change. Over here, you can see it is turning a deep blue color. So this is due to the formation of a complex or nickel ammonium complex. This nickel ammonium complex is deep blue in color. You can see the precipitate very clearly now. It's starting to dissolve starting from here. I have not given it a shake yet. So once I mix the solution properly and add a little bit of more ammonium or concentrated ammonia, you will see that this entire suspension will dissolve, or nickel hydroxide solid will dissolve and form a deep blue color solution. So let's give it a little bit of a mix and add a little bit of concentrated ammonia. You can now see very clearly we have formed a clear deep blue color solution. Now this is due to the formation of a complex with nickel 2 plus ions. Each nickel 2 plus ion form a complex with 6 ammonium ligands or ammonia ligands, forming a blue color nickel ammonium complex. So the color of the nickel ammonium complex is going to be a deep blue color solution. Let's move on to our next experiment, that is taking a nickel 2 plus ion solution and reacting it with dimethyl glyoxide. Let's take our dimethyl glyoxide solution over here and let's add a few drops of dimethyl glyoxide into our nickel 2 plus aqueous ion solution. You can see a very interesting observation here. Take a look at this observation. Upon addition of DMG or dimethyl glyoxide, the nickel 2 plus solution started forming a precipitate. So this is a very specific test to identify nickel 2 plus ions. This test answers only to nickel 2 plus and it forms a cherry red precipitate. This is referred to as a cherry red precipitate. As you can see here, when DMG is added, dimethyl glyoxide is added to nickel 2 plus aqueous ion solution, it forms a cherry red color precipitate. If you give it a little shake, you can see the precipitate particles will spread throughout the solution, forming a suspension. But if I keep holding on to it for a while, you can see the precipitate starts to get collected at the bottom. Right? So this is a very specific test to identify nickel 2 plus ion solutions or aqueous ion solutions with the use of DMG. So that brings us to an end with nickel 2 plus ion solutions. Let's have a small summary of what we observed here. We started with nickel 2 plus aqueous ion solution, and then to this we added sodium hydroxide and we saw the formation of a green color precipitate, which is NaOH twice or nickel hydroxide, which is a green color precipitate. You can see, since I have been leaving this out for a while, the precipitate is starting to collect at the bottom. And upon addition of excess amount of sodium hydroxide, we saw that the precipitate did not dissolve. This is due to the fact that nickel hydroxide is not an amphoteric hydroxide. Then we added ammonium hydroxide or dilute ammonia into nickel 2 plus ion solution. We saw that it formed the same nickel hydroxide precipitate initially. But upon addition of concentrated ammonia, we saw the precipitate dissolved. The initial precipitate looked like this, but upon addition of concentrated ammonia, we saw the precipitate dissolved to form a nickel ammonium complex. Each nickel 2 plus ion was connected to 6 ammonia ligands, forming a nickel ammonium complex, which is deep blue in color. Let's finally observe what happened when we added DMG, dimethyl glyoxime, to a nickel 2 plus ion solution. You saw the formation of a cherry red precipitate. And this, as I told you earlier, is a very specific test to identify nickel 2 plus ion solutions. So that brings us to an end with the identification tests for nickel 2 plus aqueous ion solutions. Let's move on to Fe2 plus ion solutions. In the second part of this experiment, we will take a look at Fe2 plus aqueous ion solutions and the tests for the Fe2 plus aqueous ion solution. So First, observe that Fe2 plus aqueous ion solutions have a very light green color, or we'll say pale green color in the solution. So to continue with this experiment, we will need a lot of Fe2 plus aqueous solution. So we will dilute this solution a little bit. Right. Now let's take small amounts of Fe2 plus solution into a few boiling tubes. Right. Now, we'll take the first portion of our Fe2 plus aqueous solution and we will add sodium hydroxide to it and see what the observations are. We have our sodium hydroxide solution here. We will add a little bit of the sodium hydroxide into the Fe2 plus aqueous ion solution. Now, since I haven't mixed it properly yet, you can see as soon as I added sodium hydroxide, a precipitate started to form. And this precipitate has a color that is referred to as dirty green. So what you see here is a formation of ferrous hydroxide precipitate, FeOH twice. So ferrous hydroxide precipitate that you form is dirty green in color. So if I mix it up, you will be able to see the color somewhat more clearly. Now you can see the entire aqueous medium here is colored in that dirty green color. This is due to the fine precipitate particles being dispersed throughout the solution, right? Do not be mistaken and do not think that this entire solution or what we form here is a solution. What we form here is not a solution. What we form here is a precipitate, a fine precipitate that is dirty green in color. We'll add a little bit more sodium hydroxide. Now you can see the precipitate somewhat more clearly. It's mostly the fine particles that we have in the solution now that are dirty green in color. So after observing the color of the precipitate that we form, we have to now move on to adding excess amount of sodium hydroxide to see if we can dissolve this dirty green color ferrous hydroxide precipitate. Let's add an excess amount of sodium hydroxide now. I added a generous amount of sodium hydroxide. Let's mix it really well to see if the precipitate starts to dissolve. As you can see, upon addition of an excess amount of sodium hydroxide, the precipitate does not dissolve. Just to clear your doubts, we'll add a little bit more. Upon addition of excess amount of sodium hydroxide, the ferrous hydroxide precipitate does not dissolve. This is evidence that the ferrous hydroxide is not an amphoteric hydroxide. If it was amphoteric, it will react with both acids and sodium hydroxide or any alkaline solution, but the ferrous hydroxide precipitate did not react with excess amount of sodium hydroxide, proving that it is not non-photonic hydroxide. Now let's move on to addition of dilute ammonia. We will take another portion of our Fe2 plus aqueous solution and let's add dilute ammonia onto our next portion of Fe2 plus aqueous solution. You can see over here, like in the previous experiment when we added sodium hydroxide, we saw a dirty green color precipitate, and you can see the same characteristic precipitate is also formed when we add dilute ammonia into Fe2 plus aqueous ion solution. So this indicates upon addition of dilute ammonia to Fe2 plus aqueous ion solution, we are forming ferrous hydroxide. So this dirty green colored precipitates are indicative of the presence of Fe2 plus ions in the medium, and at the same time the dirty green precipitate is due to the formation of ferrous hydroxide. So to this ferrous hydroxide suspension, let's add additional amount of ammonia in the form of concentrated ammonia. To this ferrous hydroxide solid suspension, let's add a little bit of concentrated ammonia to see what the observations are. We'll take our concentrated ammonia solution and let's add small amount of concentrated ammonia into our ferrous hydroxide precipitate over here. So here we have, after the addition of concentrated ammonia onto our FeOH twice precipitate. So you can see, upon addition of concentrated ammonia, we did not observe any change. So when it comes to ferrous hydroxide precipitate, when you add excess ammonia or concentrated ammonia onto it, you will not see any change. You will see that the precipitate still remains without it changing. So now we will move on to our next part in this experiment. In this part, we will be adding potassium ferricyanide into this Fe2 plus aqueous solution. So we'll take one portion of our Fe2 plus aqueous solution and let's add potassium ferricyanide into this. So as you can see, potassium ferricyanide has a yellowish color to that reagent. So now we will be adding small amount of potassium ferricyanide into our Fe2 plus aqueous solution. Now you can see, upon adding a little bit, a very small amount of potassium ferricyanide, the Fe2 plus aqueous ion solution turned into a really dark blue color. Now this blue color is what we refer to as Prussian blue. So although it appears to be a solution, if you observe it closely, you will see what we have here is a precipitate, right? So where the two solution mixed, so I have not shaken it still, so you can see the bottom bit, we still have the previous solution, and on the top over here, the Prussian blue color that you see is due to the formation of a complex that is insoluble in water, forming a precipitate that is Prussian blue in color. If I mix it really well, you can see the entire medium turns a Prussian blue color. We'll add a little bit of water onto this to observe this color a bit more closely. It's a really dark blue color, sometimes it's difficult to observe when it is not diluted enough. So let me dilute it a bit further. I'll take another boiling tube, transfer a small amount of that Prussian blue precipitate onto a new boiling tube, and let's add a little bit of water to observe this color a bit more clearly. So over here you can see the diluted version of Prussian blue suspension we had earlier. So you can see this to be, or you might be assuming that this is a solution, but no, this is not a solution that we have formed here. Please keep in mind, what we have formed here is a Prussian blue color precipitate, and the precipitate particles, the solid particles, are so fine and they are suspended evenly in the aqueous medium, it appears to us as a solution. But keep in mind, what we form here is a Prussian blue color precipitate. So if you let it stand for a while, if you leave it out for a very long duration, you can see the fine particles sometimes get collected at the bottom, but it takes a very long time for that to happen. We will not observe it today. So what you have here is a specific test, or I could say a special test. What you have here is a special test that you can use to identify Fe2 plus ions present in a medium with the use of potassium ferricyanate. We'll take a look at another portion of our Fe2 plus aqueous ion solution and add potassium ferrocyanide into this. Now, upon addition of potassium ferrocyanide into an Fe2 plus aqueous ion solution, the observation should be a white color precipitate. You should observe a white color precipitate. However, if the Fe2 plus ion solution is not pure, if there are any impurities, especially including Fe3 plus ions, you will not observe that white color precipitate. Instead, you will see a slight pale blue color precipitate. But keep in mind at your exam, when they ask what happens when Fe2 plus is mixed with potassium ferrocyanide, you have to mention the observation should be a white color precipitate. If the Fe2 plus solution is pure, 100% pure, you will get a white color precipitate. Let's move on to our experiment. We have our potassium ferrocyanide solution here. And now let's add small amount of potassium ferrocyanide into our Fe2 plus aqueous ion solution. As you can see, we did not form a white color precipitate. That is due to this Fe2 plus aqueous ion solution being impure. It must have had some Fe3 plus ions present in it, resulting in not giving us the white color precipitate that we want to observe. Now, let's take a look at the summary of or the identification tests that we did for Fe2 plus aqueous ion solution. So, what we have here is our Fe2 plus aqueous ion solution. It's a very pale green color solution. And then we added sodium hydroxide to the Fe2 plus aqueous ion solution, and we formed a dirty green color precipitate. Right, you can see the dirty green color precipitate that is formed, and upon addition of excess sodium hydroxide, that dirty green color precipitate did not dissolve, indicating that it is not an amphoteric hydroxide. And then when we added dilute ammonia into Fe2 plus ion solution, we saw the formation of ferrous hydroxide precipitate again, which is dirty green in color. And then when we added concentrated ammonia to it, we did not see any observation. The precipitate did not dissolve, or it did not form a complex ion in the presence of concentrated ammonia. So we did not see any observation upon addition of excess ammonia or concentrated ammonia. Then we took a small amount of Fe2 plus ion solution, added to it a little bit of potassium ferricyanide. So upon addition of potassium ferricyanide, we saw the formation of a Prussian blue color precipitate. Right? You can now see, earlier on in initial view, you might have not seen the tiny particles of Prussian blue precipitate precipitating out to the bottom. But now, after I left it for a while, you can see tiny particles of Prussian blue color precipitate that is formed in the presence of potassium ferricyanide. Right? In this test tube, you can see I diluted the Prussian blue color precipitate we got upon addition of potassium ferricyanide. Now you can see it has collected at the bottom. Very clearly you can see the precipitate here. If I shake it again, you can see the formation of the initial suspension that appeared to be a solution. But now we know it is not a solution. Instead, it was indeed a precipitate that was suspended in the aqueous medium. Finally, we took a small amount of Fe2 plus solution and added to it a little bit of potassium ferrocyanide. We expected to see a white color precipitate, but we did not see a white color precipitate. Instead, we saw a light blue color precipitate formed here, and it is dispersed throughout the medium, like in the Prussian blue color precipitate we saw earlier. So this light blue color precipitate is formed due to Fe2 plus solution that we had here being impure. If the Fe2 plus solution was in fact a pure solution, the precipitate that we will see is a white color precipitate. So keep in mind, during your exams, when they ask for the observation, when you mix Fe2 plus with potassium ferrocyanide, you have to write that the observation is the formation of a white color precipitate. If there was any impurities, this white color precipitate will appear to be a pale blue color. That is in the presence of impurities. Right? So with that, we can conclude the identification tests for Fe2 plus aqueous ion solutions. Let's move on to Fe3 plus aqueous ion solutions. Let's take a look at the identification tests for Fe3 plus aqueous ion solution. So what we have here is an Fe3 plus aqueous ion solution. So in this Fe3 plus aqueous ion solution, you can observe a yellow-brown color. So the characteristic color of Fe3 plus aqueous ion solution is yellow-brown. So to better observe that color and to make sure that we have enough of this solution to carry out 5 different experiments, we will dilute this solution a little bit further. We have a wash bottle here. Let's add a little bit of water into this. You can observe the color a little bit better now. We'll have to add more water to make sure we have enough to last the entire experiment. So now let's take small portions into 5 different test tubes. Right, we have separated the initial solution into 5 different boiling tubes. Now let's go on ahead and add sodium hydroxide into a portion of our Fe3 plus aqueous ion solution. So we will take our Fe3 plus aqueous ion solution, yellow brown in color, and we will take our sodium hydroxide solution, and we will add a small amount of sodium hydroxide to this to see what happens upon addition of sodium hydroxide. You can observe upon addition of sodium hydroxide, we started forming a red-brown color precipitate. You can very clearly observe here the formation of a red-brown color precipitate. You can already see it starting to sink to the bottom, so it's sedimenting at the bottom. So let's give it a little bit of a mix to observe the color better. Now this precipitate, when I shake it like this or mix it like this, you can see the precipitate spreads throughout the solution and forms a red-brown color suspension. Over here what has happened is the fine precipitate particles, the solid particles that are really fine, has now spread throughout the medium, making the entire medium a red-brown color. But like I mentioned earlier, what we form here is a red-brown color precipitate. So that's what happened when we added a small amount of sodium hydroxide. Let's add excess amount of sodium hydroxide to see if we can dissolve this precipitate in the presence of excess sodium hydroxide. So let's add a bit more sodium hydroxide onto this. So you can see by now I have added a lot of sodium hydroxide. Let's swirl it around a little bit. Can you see any different observation? Did you see a different observation upon addition of excess amount of sodium hydroxide? The answer to that would be no. That is because addition of excess sodium hydroxide will not result in the dissolution of the ferric hydroxide precipitate that is formed here. So this brown color or red-brown color precipitate that you observe over here is ferric hydroxide, FeOH thrice. FeOH thrice or ferric hydroxide is not a an amphoteric precipitate, which means it does not react with additional amount of sodium hydroxide that is added. So this is evidence that FeOH thrice or ferric hydroxide does not dissolve in excess amount of sodium hydroxide, indicating that it is not an amphoteric hydroxide. Let's move on to the next experiment, where we will take a small portion of Fe3 plus aqueous ion solution, and to that we will be adding dilute ammonia. We have here our dilute ammonia solution, and we will add a little bit of dilute ammonia onto our Fe3 plus aqueous ion solution. You can see, just like in the previous example or experiment, you can see the formation of a precipitate. The entire solution turned cloudy. This is due to the dilute nature of ammonia over here. We don't see a drastic formation of the precipitate, but if I add a little bit more ammonia, you'll be able to observe it a little bit more clearly. So upon addition of ammonia, what we have here is the formation of ferric hydroxide. So initial solution appeared to be yellow-brown in color, right? This on my left hand, what you see here is Fe3 plus aqueous ion solution, and on my right, what you see here is the ferric hydroxide precipitate that is formed upon the addition of dilute ammonia. So here also, like in the previous experiment, we have formed FeOH thrice, which is red-brown in color. Now let's move on to adding a little bit more ammonia onto this mixture to see if concentrated ammonia can dissolve the precipitate that is formed here. So if the ferric hydroxide precipitate can form a complex ion with concentrated ammonia, at that point this precipitate will dissolve. But if it can't, you will see no observation. Now I am adding concentrated ammonia onto this. Please observe what happens. I added a generous amount of concentrated ammonia. Do you see any observation? After the addition of concentrated ammonia, do you see any observation? The answer would be no. We do not see a different observation upon the addition of concentrated ammonia. All you see is the red-brown precipitate formed due to the presence of ammonia in the medium. What you have here is ferric hydroxide, FeOH thrice, that is formed, which is a red-brown color precipitate. Right, so now since the medium is somewhat more diluted, you can see the precipitate collecting at the bottom. So over here, the red-brown color precipitate you see is ferric hydroxide. Let's take another portion of our Fe2 plus ion solution, and to that we'll be adding potassium ferricyanide. So we have our potassium ferricyanide solution here, which is a yellow color solution. We'll take our potassium ferricyanide and we'll transfer a small amount of potassium ferricyanide into our Fe2 plus aqueous ion solution. As you can see, upon the addition of potassium ferricyanide, what you see here is a formation of a brown color solution. Over here, we do not form a precipitate. To see the coloration, brown coloration a little bit more clearly, let's add a little bit of water. You can see the brown coloration of the solution. Upon addition of potassium ferricyanide into the Fe3 plus aqueous ion solution, what you form is a brown color solution, and you will not observe a precipitate being formed. There will be no precipitate, and the solution will turn into a brown color. Let's take another portion of our Fe3 plus aqueous ion solution over here, and to it we will add potassium ferrocyanide solution. You have our potassium ferrocyanide solution over here. Let's observe what happens upon the addition of potassium ferrocyanide onto our Fe3 plus aqueous ion solution. As you can see, upon addition of potassium ferrocyanide to Fe3 plus aqueous ions, you formed a precipitate here. Although this appears to be a deep blue color solution or Prussian blue color solution, what you see here is a Prussian blue color precipitate. So let's see this color a little bit more clearly by diluting this a bit more. We'll take our wash bottle and we will add a small amount of water to observe this color a little bit more clearly. So this is a suspension of Prussian blue color precipitate, but due to these fine precipitate particles being dispersed in the medium, we see this entire aqueous medium a deep blue color or Prussian blue color. But if you leave it out for a period of time, you will see tiny Prussian blue color precipitate particles collecting at the bottom of the boiling tube, and that is due to the tiny or fine nature of the precipitate that is formed here. So what we have here again is a Prussian blue color suspension or precipitate. Finally, let's move on to another portion of our Fe3 plus aqueous ion solution. We have here our last portion of Fe3 plus aqueous ion solution, and to this we will be adding potassium thiocyanate. This clear solution we have here is potassium thiocyanate. Now this experiment that I'm about to do is a very specific experiment for Fe3 plus ions. Let's observe what happens when we add potassium thiocyanate into Fe3 plus ions. I hope you can see this observation. What we form here is a solution, but I have not mixed it yet. Upon the addition of potassium thiocyanate to Fe3 plus ions, you form a dark red color, or sometimes it is referred to as blood red color solution. So what you see here is a blood red color solution being formed when potassium thiocyanate is added to Fe3 plus ions. So let's mix it a little bit. You can see this solution is now a blood red color solution. You will not observe any precipitate. What you see here is a blood red color solution. Let's dilute it a little bit to see this color a bit more clearly. As you can see, this is a blood red color solution. Since the color of the solution is not very clear in camera, we'll dilute this a little bit further and then observe the color properly. Now you can see that this solution is red in color, but as soon as it formed, it was a darker red before I diluted it, so that is why it is referred to as a blood red color solution will be formed. Right, students? So with that, we come to an end of the identification tests that is there for Fe3 plus aqueous ion solution. Let's take a look at the summary. Students, we started with a yellow brown color Fe3 plus aqueous ion solution, and to that we added sodium hydroxide and formed a ferric hydroxide precipitate. You can see the comparison here. So the ferric hydroxide precipitate was red brown in color. You can see the precipitate has now collected at the bottom. We left it there for a while for the precipitate particles to collect at the bottom. So you can see now the yellow brown color solution we had, upon reacting with sodium hydroxide, turned ferric hydroxide, which is a red brown color precipitate. In the second part of the experiment, we took an Fe3 plus aqueous ion solution and we added dilute ammonia to it. So the result was the formation of red-brown precipitate like in the previous experiment. So upon addition of concentrated ammonia as well, we noticed that this red-brown color precipitate that we have formed did not dissolve. In the previous experiment, upon addition of excess sodium hydroxide also, we saw that the red-brown precipitate did not dissolve. In the case of sodium hydroxide, it was evident that the red-brown precipitate did not dissolve because the ferric hydroxide precipitate that was formed was not amphoteric. In the case of concentrated ammonia, the reason why the red-brown precipitate did not dissolve, or ferric hydroxide precipitate did not dissolve, because it did not form a complex with the ammonia that is present in the medium. In the third part of the experiment, we took Fe3 plus ion solution and added potassium ferricyanide. Upon addition of potassium ferricyanide, we saw that the Fe3 plus ion solution turned into a brown color. We did not form a precipitate here. What we did was the formation of a brown color solution. So upon addition of potassium ferricyanide to Fe3 plus ion solution, the observation was formation of a brown color solution. Later on, we took a small portion of Fe3 plus ions and added potassium ferrocyanide. Upon addition of potassium ferrocyanide, we formed a Prussian blue color precipitate. So this precipitate is formed when potassium ferrocyanide is added to Fe3 plus ions. And finally, in a very specific chemical reaction to identify Fe3 plus ions, we took a small portion of Fe3 plus ion solution and added potassium thiocyanate to it. The result was formation of a blood red color solution. You can see here the solution is blood red color. So this is a very specific chemical reaction to identify Fe3 plus ions. So upon addition of potassium, thiocyanate, Fe3 plus ion solution will convert into a blood red color solution. You will not observe a precipitate here. The solution that you form is going to be blood red in color. So students, that is all for the identification test for Fe3 plus aqueous ion solutions. Let's move on to copper 2 plus ion solutions. Let's take a look at the identification test for Cu2 plus or Cu2 ions. In this experiment, we will have our copper 2 plus aqueous ion solution. Right, so you can see the copper 2 plus aqueous ion solution is a bright blue color. So to this aqueous copper 2 plus ion solution, we'll add a little bit of water so that we can separate it into 3 different portions and carry out our experiments. So let's take a wash bottle and add some water to dilute this solution. Now we have a dilute copper 2 plus aqueous ion solution. We'll transfer small amounts into 3 different boiling tubes. To a small portion of our copper 2 plus aqueous ion solution, we will add a small amount of sodium hydroxide. Let's see the observation when we add small amount of sodium hydroxide onto our copper 2 plus solution. We have our sodium hydroxide here. We'll add a small amount of sodium hydroxide here. Now you can very clearly see, upon addition of sodium hydroxide, the formation of a blue color precipitate. So this blue color precipitate you see over here is copper hydroxide or cupric hydroxide, or in other words, copper 2 hydroxide. Formula would be CuOH twice. So this cupric hydroxide is blue in color. If I shake it a little bit, you can see this blue color fine precipitate will disperse throughout the aqueous media and will form a uniform colored suspension over here. It's a pale blue color suspension, you see. Now, what we are going to do is add excess amount of sodium hydroxide to see if the copper hydroxide precipitate will dissolve in excess amount of sodium hydroxide. So we'll have our sodium hydroxide here, and we'll add excess amount of sodium hydroxide to this. You can't see the precipitate dissolving here. All that happened was increasing the precipitate because we initially had a very small amount of sodium hydroxide. But upon addition of more and more sodium hydroxide, you can see the precipitate that was formed does not dissolve. So the pale blue color cloudy nature of the suspension remains. This is due to the fact that copper hydroxide or the precipitate of copper hydroxide does not dissolve in excess amount of sodium hydroxide. Now let's move on to the second test, that is, we'll take a small amount of copper 2 plus aqueous solution and we will add dilute ammonia. So we have our dilute ammonia here. let's add a small amount of dilute ammonia onto our copper 2 plus solution. You can see, like in the previous experiment, upon addition of a small amount. Now the reason why I have added a small amount is to very clearly see the precipitate being formed here. So we have the precipitate being formed over here, where dilute ammonia came into contact with our copper 2 plus aqueous ion solution. So a pale blue color precipitate forms here in the copper 2 plus ion solution. So what you see here is copper hydroxide, or what is referred to as cupric hydroxide, CuOH twice. So we'll go on ahead and add adequate amount of dilute ammonia to make sure we produce enough of the precipitate. Now you can see that the fine precipitate particles have gotten dispersed throughout this aqueous medium, and it appears to be a pale blue color suspension of the copper hydroxide precipitate. As a second step to the same experiment, we will add a small amount of concentrated ammonia. We need to see if the copper hydroxide that is formed here will dissolve in the presence of concentrated ammonia. If it dissolves, that means it forms a complex ion with concentrated ammonia. Let's move on ahead and do that. Let's take concentrated ammonia and very slowly let's add concentrated ammonia along the walls of this boiling tube. So I want you to make this observation. You can see when concentrated ammonia is added, as soon as the precipitate comes into contact with the concentrated ammonia, it forms a blue color solution. This is due to the copper hydroxide dissolving in the concentrated ammonia, forming a copper ammonium complex. So one copper 2 plus ion forms 4 coordinate bonds with 4 ammonium or ammonia molecules and forms a complex that is blue in color. It's a deep blue color complex that is formed, right? So this is not a precipitate, this is a solution that is formed. So one copper 2 plus ion forms a complex with 4 ammonia molecules forming a deep blue color complex that you observe here. So you can see slowly the dissolving of copper hydroxide, CuOH twice. It slowly dissolves to form a deep blue color solution. Let's now mix it really well to see if the rest of the precipitate, you can see the precipitate here, copper hydroxide precipitate. Let's see if the rest of the precipitate can also be dissolved. We'll need more concentrated ammonia. Now we can observe in the presence of concentrated ammonia, the copper hydroxide that was initially precipitated dissolved and formed a deep blue color solution, forming a complex between copper ions and ammonia molecules. Let's move on to the final test that is there to identify copper 2 plus ions. That is by adding a small amount of potassium ferrocyanide into copper 2 plus aqueous ion solution. So let's take a small amount of copper 2 plus aqueous ion solution and add a small amount of potassium ferrocyanide. So this test is also specific to copper 2 plus. This test is also specific to copper 2 plus ion solutions. So let's see what the observation is. As you can see, when we add potassium ferrocyanide into Cu2 plus aqueous ion solution, we form a very interesting precipitate. So this is a characteristic reaction or specific reaction you can do to identify a solution of copper 2 plus. So what you see here is a chocolate brown color precipitate that is being formed. So this test can be specifically used to identify a solution of a copper 2 plus aqueous ion solution. So what you see over here is that chocolate brown color precipitate. Let's give it a shake so you can see it being mixed very clearly. The chocolate brown color is now very clearly seen after mixing the two reagents together, right? So initially what I showed you was upon addition of potassium ferrocyanide without mixing the mixture. Now after you mix it, you can very clearly see the chocolate brown color precipitate that is formed. We can add a little bit of water to further see the color. Right? So the chocolate brown color precipitate is formed, right? So this is a specific reaction that is done to identify copper 2 plus ions. So we have now concluded the test that is there to identify copper 2 plus ion solutions. Let's take a look at the summary. First, we observe the color of copper 2 plus aqueous ion solution, which is a blue color solution. And to that, we added a small amount of sodium hydroxide and then try to dissolve it in excess amount of sodium hydroxide. But the precipitate did not dissolve. So what we formed was a blue color precipitate. Now the precipitate particles are suspended in this aqueous medium. That is why it appears cloudy, and therefore what you see here is the copper hydroxide precipitate, right? So this precipitate did not dissolve in excess sodium hydroxide. And then we took ammonium solutions, and then we took dilute ammonia and added it to copper 2 plus aqueous ion solution. Initial observation was the formation of copper hydroxide precipitate, which is pale blue in color. And then when we added concentrated ammonia, we were able to dissolve the copper hydroxide precipitate and form a deep blue color solution. And we learned that this is happening due to the formation of a copper ammonium complex. One copper 2 plus ion formed a complex ion with 4 ammonia molecules, and that complex is a deep blue in color. And finally, we took a copper 2 plus aqueous ion solution and we added to it potassium ferrocyanide. So this experiment was a specific experiment to identify copper 2 plus aqueous ion solutions. And you can see upon addition of potassium ferrocyanide, the solution turned into a chocolate brown color precipitate. So you see over here, what you see over here is a chocolate brown color precipitate formed after the addition of potassium ferrocyanide to copper 2 plus ions. That is all for the identification test for copper 2 plus. Let's move on to our final D block element, which is chromium 3 plus ions. Finally, let's take a look at chromium 3 plus ion solutions and the identification tests for chromium 3 plus ions. What you see here is chromium 3 plus aqueous ion solution. And as you observe here, the color of that is a green color. Like in the previous experiments, let's transfer small amounts of this chromium 3 plus ion solutions into different boiling tubes. First of all, let's dilute it a bit further and then transfer it into different boiling tubes. We will take our wash bottle, we'll add a little bit of water and dilute it like this. And let's transfer small amounts into 3 boiling tubes. Now, let's move on to our first experiment. So, in our first experiment, what we are going to do is add a small amount of sodium hydroxide onto our chromium 3 plus aqueous ion solution and note our observations. When you add sodium hydroxide, very slowly onto this, but be very careful and only add a very small amount of sodium hydroxide. You can see upon addition of a small quantity of sodium hydroxide, a green color precipitate has started to form. I have not yet mixed it. I haven't mixed it yet because I want you to observe the precipitate very clearly, because after mixing it, it will appear to be a suspension, so you will not be able to properly see the precipitate. So over here, what you see at the bottom is the chromium hydroxide, CrOH thrice. It's a green color precipitate. So now if I mix it, you can see the precipitate kind of gets mixed in the aqueous medium, forming a suspension like this. Now let's see what happens if we add excess amount of sodium hydroxide. Now you can see the precipitate that was formed earlier is slowly dissolving in excess amount of sodium hydroxide. So if I mix this really well, you can see all of the precipitate that we saw earlier dissolved to form a clear solution. Earlier on, we had chromium hydroxide, CrOH thrice. Over here, what you have is a solution that is formed where chromium ions, Cr3 plus ions, forms a complex with 6 OH minus ligands. So with 6 hydroxide ligands, when Cr3 plus forms a complex, that complex is a blue color solution. right? So the observation here is that chromium hydroxide is dissolving in excess amount of sodium hydroxide, forming a green color solution back again. Let's move on to addition of dilute ammonia. So we will take our chromium 3 plus ion solution and we will be adding dilute ammonia onto this. So we have our dilute ammonia solution over here, and to this let's add a small amount of dilute ammonia. So we'll add small amount of dilute ammonia onto our chromium 3 plus ion solution. So when you very carefully add it, you can see the formation of the green color precipitate. So with dilute ammonia as well, you can see the formation of a green color precipitate. Like in the previous experiment, what you see here is chromium hydroxide, CrOH thrice, right? Or chromium 3 hydroxide. Let's add a little bit more of that to make sure that all of it is converted into chromium hydroxide. Right. Now students, after forming this chromium hydroxide precipitate, we need to see if this precipitate can dissolve in excess ammonia. So what we do is we use a more concentrated ammonia solution and we will add concentrated ammonia onto this precipitate to see if this precipitate dissolves in the presence of concentrated ammonia. We have our concentrated ammonia here and we will be adding concentrated ammonia onto our chromium hydroxide precipitate. We have a lot of solution formed here. You can see the color of the precipitate changed. So let me transfer some amount into a different boiling tube so that we actually can see the color change very clearly. As you can see, when we added concentrated ammonia onto chromium hydroxide, the precipitate dissolved to form a violet solution. Sometimes the color that we see over here might not be very clear to you, but what we see here is a violet color solution being formed. So precipitate did dissolve to form a violet solution due to the formation of an ammonium complex with chromium ions. Chromium ions forms a complex with ammonia to form this violet color solution. So each chromium ion, chromium 3 plus ion, forms 6 coordinate bonds with 6 ammonium molecules to form a complex that is violet in color. This is a solution that you see over here. To better observe the colors, we'll have to leave it aside for a while because this reaction is quite slow. So we will observe the proper colors after a while. When I am discussing the summary, you might observe a better violet color. Let's finally take a look at a very specific test that is there to identify Cr3 plus aqueous ion solutions. That is, when you react chromium ion solutions after making the medium alkaline, if you add hydrogen peroxide, you can convert the Cr3 plus ions into chromate ions, CrO4 2 minus. So the chromate ions are yellow in color. So we can now convert Cr3 plus aqueous ion solutions that we have over here. So we have the Cr3 plus ion solution over here. We first have to make this medium alkaline by adding a small amount of sodium hydroxide, and then to that we will add hydrogen peroxide and convert. Now hydrogen peroxide is a good oxidizing agent, so it will convert this chromium 3 plus into chromate ions. So chromium 3 plus will be oxidized to become chromate ions, CrO4 2 minus, which is a yellow color solution. So let's add a small amount of sodium hydroxide and make this medium basic. Now we have made the chromium 3 plus ion solution alkaline by adding sodium hydroxide. To that we will add hydrogen peroxide. We have a hydrogen peroxide bottle over here. You can see that it is present in a darker color bottle to make sure that it does not decompose in the presence of light. We'll add a small amount of hydrogen peroxide to see what happens. You can see upon addition of hydrogen peroxide, we started a reaction where the color of the chromium ions that we had earlier, the green color, disappeared, and now it appears to be a darker orange color. However, this is due to the solution being extremely concentrated, so we will now dilute the solution to observe the right color change, which is obtaining a yellow color. If you take a small amount of this initial solution, add a little bit more sodium hydroxide, and a few drops of hydrogen peroxide, at this point you can see the formation of a yellow color. We can further dilute this to observe the color change properly. Let me dilute it a little bit further. Now we have a yellow color solution that is formed due to the presence of our chromate ions here, which is CrO4 2 minus. So by adding sodium hydroxide and hydrogen peroxide onto Cr3 plus aqueous ion solution, we have converted the chromium ions or Cr3 plus ions into CrO4 2 minus, or in other words, chromate ions, which are yellow in color. Students, that is all for the identification tests of chromium 3 plus ion solutions. Let's take a look at the summary. We started off with chromium 3 plus aqueous ion solution, which was green in color. And then to that we added sodium hydroxide. So this test tube, or boiling tube rather, that we have here contains chromium 3 plus ion solution that was added with sodium hydroxide. Upon addition of sodium hydroxide initially, we saw the formation of a green color precipitate, which is chromium hydroxide. But on further addition of sodium hydroxide, we saw that this green color precipitate dissolved to form a green color solution, meaning chromium hydroxide showed amphoteric behavior. Then, secondly, we took a small amount of our chromium 3 plus aqueous ion solution and added dilute ammonia onto it. Just like we initially started to add sodium hydroxide, with dilute ammonia, we saw the formation of a green color precipitate. So what we saw being formed there was chromium hydroxide, which is a green color precipitate. Afterwards, we added concentrated ammonia onto that. Upon addition of concentrated ammonia, that green color precipitate dissolved to form a violet solution. This is due to the chromium ions forming a complex with ammonium molecules present here in the medium. So what you are observing here is a chromium 3 plus ion forming a coordinate, actually forming 6 coordinate bonds with 6 ammonium molecules and forming a complex ion. So that complex ion is violet in color. You can see the precipitate has dissolved now and formed a clear violet solution. The chromium ammonia complex is going to be a violet color complex. Finally, students, as a specific test designed to identify chromium 3 plus ions, we took a small amount of chromium 3 plus aqueous solution and reacted it with sodium hydroxide and hydrogen peroxide. So we initially added small amount of sodium hydroxide to make the medium alkaline, and then we added the oxidizing agent hydrogen peroxide to oxidize chromium 3 plus into chromate ions. Now chromium 3 plus aqueous ions are green in color and chromate ions are yellow in color. So we saw upon addition of sodium hydroxide and hydrogen peroxide, the chromium ions turned into chromate ions. So you can see chromium ions are green in color and the chromate ion solution is yellow in color. This experiment is specific to chromium, so whenever you need to identify chromium ions present in a medium, you can use this experiment as well. With that, we conclude the tests that are there for chromium 3 plus ion solutions. Now, we will be moving on to discussing further important theory parts and some questions related to this practical number 23. Let's move on to that now.
Students, let's take a look at some questions revolving around the practical 23. Now, we looked at the theory parts revolving around practical 23 and we went into the lab and conducted the practical. Now, we are focusing on some questions. So, let's take a look at the first question. Now, in the first question, they ask us about M, or an element called M. M is a 3D transition element. Each atom of M contains 6 unpaired electrons. And then they ask us to identify M, write the full electronic configuration of M, write the balanced chemical equation for the reaction when M3 plus ion solution is reacted with sodium hydroxide and H2O2. So now we indirectly know that M forms a 3 plus ion. What is the color change observed in the reaction above? Name 2 other compounds of M that have the same oxidation state and name 1 use of M. So this question is revolving around an element called M, which contains 6 unpaired electrons. So that is a very important detail. It contains 6 unpaired electrons. Now students, let's move on to discussing the answer to the first part here. So if you have 6 unpaired electrons in an element, what could it be? Now, by now, you should have a good understanding about different types of electronic configurations in the 3D elements. So they say this is a 3D transition element. So obviously, if a 3D element has unpaired electrons, it is going to be a transition element. So if you are writing the electronic configuration of 3D transition elements, you come across a situation where you get 3D5 and 4s1. Now, this is the electronic configuration of chromium. Now, chromium has this electronic configuration. If you take a look at how electrons are present in the chromium atom, you can see there are 5 3D electrons in the 3D subshell, and each orbital contains only 1 electron. And when it comes to the 4s subshell, you have 1 electron in it. Altogether, 6 unpaired electrons are there. So we are basically talking about chromium here. So chromium has a very special electronic configuration. It should originally be 3D4, 4s2. However, since it's a very special electronic configuration, we tend to remember this. It is 3D5, 4s1. Similarly, copper also have a bit of a special electronic configuration. 3D9, 4s2 is the electronic configuration copper should originally have if it followed the trend. However, it is not having that electronic configuration. Copper's electronic configuration happens to be 3D10, 4s1. So similarly, chromium's electronic configuration is very familiar to us. So when they say there are 6 unpaired electrons, you should know that we are talking about chromium. So the identity of M is this. M is our chromium metal. Now let's move on to the next question. Now in the second question, you can see, write the full electronic configuration of M. So if you're writing the full electronic configuration, we have 1s2, 2s2, 2p6, 3s2, 3p6. Then we have 3D, but before filling the 3D, we normally fill 4s, 4s1, 3d5. Now we already discussed the electronic configuration of chromium. So this is the full electronic configuration of chromium. So if you have written this for a question like this, you would get full marks. Now some students would change these two up and write like this: 4s1, 3d5. Although this is not necessarily incorrect, it is preferred if you can keep 3d5 and then 4s1. Now let's take a look at the third question. Write the balanced chemical equation. Write the balanced chemical equation for the reaction when M3 plus ion is reacted with sodium hydroxide and hydrogen peroxide, and use the actual chemical symbol of M. So now students, we have to remember the practical we did. In the practical, we observed when chromium 3 plus ion solutions are reacted with hydrogen peroxide in a strongly alkaline medium, what happened? Chromium 3 plus gets oxidized to chromate ions. Chromium 3 plus ions got oxidized to chromate ions. So we can see Cr3 plus ions getting oxidized to chromate ions, CrO4 2 minus. Now chromium 3 plus ions, what was the color? It was a green color solution, and chromate ion solution was a yellow color solution. And what we used here was hydrogen peroxide. in strong alkaline medium. So if you observe here, the oxidation number of chromium is +3 and oxidation number of chromium in the chromate ion is +6. Now if you are unsure of how we got to that oxidation number, we can actually show it to you here. So if you take chromium, oxidation number to be X, this is what you don't know. And then if you write down, or if you do this calculation, you know, if you add all the oxidation numbers, it should be equal to the charge that is seen in the ion. So we have oxidation number of chromium, which we don't know, considered to be X, and there are 4 oxygen atoms, and each oxygen here has an oxidation number of -2, and the overall charge of the ion is -2. So if you solve this, it becomes X minus 8 is equal to -2. X is equal to 8 minus 2, which is going to be +6. So oxidation number of chromium here, when it comes to the chromate ion, is +6. Now students, you can see this is an oxidation. So as you can see, it is oxidizing from +3 to +6. So the overall balanced chemical equation for this reaction is going to be Cr3 plus, we will need 2 of them, plus 3H2O2 plus 10 OH minus, plus 10 OH minus, turns into 2 CrO4, 2 minus, and 8 H2O. So this is the balanced chemical equation. This is our balanced chemical equation for this reaction. Chromium ions or chromium 3 plus ions goes and turns into chromate ions. Again, if you are taking a look at the oxidation number, it is going from +3 to +6, which is an oxidation. And then you can see we have oxygen going from -1 to -2. If you wish to take a look at the half equations, chromium 3 plus ions turn into chromate ions. Our oxidation number here is +3 and oxidation number here is +6. We calculated this earlier. And when one chromium 3 plus ion turns into chromate ions, 3 electrons have to be removed. As you can see, we are going from +3 to +6. So therefore, we can say around 3 electrons were removed. So we can indicate the 3 electrons on the right hand side to denote that electrons were removed. So overall charge now on the left hand side is going to be +3. On the right hand side, it is -5. On the right hand side, it is -5. There are 3 electrons and the chromate ion charge is -2. And there are 3 electrons altogether, -5 charges there. But on the left hand side, it's +3. So now we have to balance the charges. So if you're trying to balance the charges, you have to make sure that you add an ion that is already there in the medium. So we have OH minus ions, enough and more of OH minus ions in the medium, because we are conducting this experiment in alkaline medium. So we can add OH minus ions. How many of them should be added? So we need to make sure that the left hand side of the equation also gets to -5. So in order to do that, we have to add 8 hydroxide ions. So at this point, 8 negative charges along with 3 positive charges will bring the overall charge on the left hand side to -5. So -5 on the left hand side, -5 on the right hand side, charges are balanced. And finally, what is left for us to do is now balancing of the hydrogens and the oxygens. So if you take a look at the hydrogens here, there are 8 hydrogens and 8 oxygens. 4 oxygens are already taken into account when it comes to our chromate ion. So therefore, if you add 4 water molecules, the number of oxygens are going to be balanced. Let's call this our equation number 1. Or this is going to be our oxidation reaction. This reaction is our oxidation reaction. Now, let's move on to our reduction reaction. So we have hydrogen peroxide, H2O2. Now there are 2 oxygens turning into 2 hydroxide ions. Here the oxidation number is -1. Here the oxidation number is -2. So there's a gaining of 2 electrons here. 2 electrons are gained here. Now at this point, this is already balanced. You can see there are 2 hydrogens on the left hand side, 2 hydrogens on the right hand side, 2 oxygens and 2 oxygens on the right hand side as well. And the overall charge on the right hand side is -2, and overall charge on the left hand side is also -2. So therefore, this reaction is also currently balanced. This is going to be our reaction number 2, which is our reduction reaction. So the first one is oxidation and the second one is a reduction. Now we can get to the balanced chemical equation by adding these 2 reactions together. If you add these 2 reactions together, we can get to the balanced chemical equation. Now if you pay attention here, you would see the number of electrons do not necessarily match here. The first reaction releases 3 electrons, the second reaction takes up only 2 electrons. So therefore, we have to make sure we multiply the first reaction by 2 so that the first reaction ends up releasing 6 electrons, and the second reaction should be multiplied by 3 so that it ends up gaining altogether 6 electrons. Second reaction is going to be multiplied by 3. So the final equation that you would obtain when you do this, we'll focus on chromium first. We'll get, when you multiply it by 2, we'll get 2 chromium 3+ ions along with 3 H2O2. And you can see on the left hand side there are 8 hydroxide ions. If you multiply that by 2, it's going to be 16. But there are hydroxide ions on the second equation as well. There are 2 of them on the right hand side. So if you multiply that by 3, it's going to be 6. So you know whatever that is on the left hand side can get cancelled off by what is on the right hand side of the second equation. So therefore 16 subtracted by 6 is going to leave us with 10 hydroxide ions. And then we have 2 chromate ions. You multiply these water molecules. There are 4 water molecules. You have to multiply it by 2. So we have 8 water molecules there. And on the second equation, the hydroxide ions that were produced were already cancelled. So therefore, now if you take a look at it, you can see we have obtained the same balanced chemical equation. 2 chromium 3+ ions, 3 hydrogen peroxide, 10 hydroxide ions along with 2 chromate and 8 water molecules are produced. Right, so when it comes to a question like this, it is important to know how to write the balanced chemical equations. If you happen to be someone who wants to remember these type of equations, you can go ahead and do that as well, because some questions, they don't ask you to show how you obtain this answer. Sometimes they only want the equation. So 2, 3, 10. 2 chromium 3 plus 3 hydrogen peroxide along with 10 hydroxide ions, when reacted together, will form 2 chromate and 8 water molecules. Let's move on to the fourth question. In the fourth question, they're asking you, what is the color change observed in the reaction above? So what is the reaction that happened above? We saw chromium 3 plus aqueous ion solution turned into chromate ions when reacted with hydrogen peroxide in a strong alkaline medium. We formed chromate ions. What is the color of chromium 3 plus aqueous ion solution? We saw in the practical that we conducted in the lab, chromium 3 plus aqueous ion solutions are green in color. And what is the color of chromate aqueous ion solutions? Chromate aqueous ion solutions are yellow in color. What about dichromate? Dichromate is orange in color. So we are actually forming here a chromate ion when you are reacting the chromium 3 plus aqueous ions with hydrogen peroxide, and when you react hydrogen peroxide in alkaline medium, chromium 3 plus ions convert into chromate ions. Color change that you observe is from green to yellow. Color change you observe is a green color solution is turning into a yellow color solution. Now let's move on to our next slide. The fifth question asks us to name 2 other compounds of M that have the same oxidation number as the product formed in the question number 3. So in the question number 3, we formed the chromate ion, CrO4 2-, and we observed the oxidation number of the chromium atom here is +6. So what are 2 other compounds? They're asking for other compounds with the same oxidation state. Other compounds. If you take a look at these compounds, you may already know one of the compounds that is having the same oxidation number. Before I move on to the compound, I will talk about the ion that has the same oxidation number. You know, chromium ions can be turned into chromate. We already saw that reaction. But at the same time, chromate ions have an equilibrium with dichromate ions. So dichromate ions and chromate ions both have the same oxidation number. So if you take a compound that contains the dichromate ion, for example, in the lab, we always have potassium dichromate, Cu2 Cr3 So the oxidation number of chromium in dichromate is going to be +6. So you have here our dichromate, which contains the oxidation number +6. And then we have an oxide like this, CrO3. CrO3 also contains the oxidation number +6. Apart from that, we have a very volatile liquid called chromyl chloride. So this is named chromyl chloride. A very volatile liquid. compound again having the oxidation number +6 in chromium. So chromine chloride also contains the oxidation number +6 on chromium. So these are 3 compounds that contain +6 oxidation number for chromium. With that, we can move on to the next question. Name one use of M. Name one use of M. So chromium metal is actually used in forming alloys, especially stainless steel. So one of the very important uses of chromium would be that forming stainless steel or forming alloys. And another use of chromium is chromium plating or electroplating. You might have seen different metal objects plated with chromium. So electroplating of chromium is also another use of chromium. If you have mentioned at least one of these, that will be correct. With that, we can move on to our next question. In the next question, this is the second question, students. They are asking about an element called A. Let's take a look at that question. A3 plus iron solution, an A3 plus iron solution is reacted with a small amount of sodium hydroxide. Alright, and then we have a green color precipitate B was formed. So this question is giving us information about iron solution that has A3 plus ions, and when it is reacted with sodium hydroxide, it forms a green color precipitate, and that precipitate was named B. When excess sodium hydroxide is added, the green color precipitate dissolves to form a green color solution. Right, so in excess sodium hydroxide, it dissolves. What type of precipitates, what type of hydroxides dissolve in excess sodium hydroxide? If you said amphoteric hydroxide, you are correct. So we are dealing with a metal ion that forms amphoteric hydroxides. When a small portion of a green precipitate B is heated, a green color solid was formed. When a green color precipitate was heated, a green color solid was formed. By now, you might have an idea what metal we are talking about. When it comes to green color precipitates, right? So we'll first of all, before we move on to the question, we'll move on to identifying what is happening here. So we have a green color hydroxide formed. What are the green color hydroxides that you know of? We know that Fe2 plus aqueous ion solutions are green in color. We looked at it in this particular experiment. And we have nickel hydroxide. So before we move on to nickel, we'll focus on Fe2 plus. So Fe2 plus aqueous ions, when reacted with hydroxide, will form ferrous hydroxide, which is a green color precipitate. This is not just any green, it is referred to as dirty green. It's a bit of a darker green color precipitate. And then we have nickel. Nickel 2 plus ion solutions are also green in color, and when you react it with sodium hydroxide, it forms a nickel hydroxide, which is also going to be a green color precipitate. Apart from that, we have another metal, chromium 3 plus. We looked at it earlier as well. Chromium 3 plus aqueous ion solutions are green in color. When you react them with sodium hydroxide, you will see they will also form chromium hydroxide, which is going to be a green color precipitate. So we have an idea about what ions might qualify to be A3 plus. So Let's move on to this page and we'll list down the green color precipitates that we know of. We know Fe2 plus can turn into FeOH2, which is a hydroxide which is green in color. And then we have nickel 2 plus, which is going to form nickel hydroxide, again which is green in color. And finally, we come across chromium 3 plus. We form chromium hydroxide, which is also going to be green in color. Now, due to a few reasons, we can actually find out what the answer is. Fe2 plus ions and nickel ions, when they react with sodium hydroxide to produce ferrous hydroxide and nickel hydroxide, although these precipitates are green in color, they are not going to dissolve in excess sodium hydroxide. Both ferrous hydroxide and nickel hydroxide does not dissolve in excess sodium hydroxide. However, chromium hydroxide does dissolve in excess sodium hydroxide. So if you add just a little bit of sodium hydroxide, you will be forming chromium hydroxide here. And then if you add excess sodium hydroxide, then what you will be forming is a complex ion, which is CrOH4, and the overall charge is minus. This is also a green color solution. So students, at this point, we can identify that A3 plus. And another indication would be, they say the ion has 3 plus charge. Fe2 plus and nickel 2 plus is both having a 2 plus charge. But when it comes to chromium, it has a 3 plus charge. So we can be sure the A3 plus they are talking about in this question is in fact chromium 3 plus ions. So the answer to this question is chromium 3 plus. Chromium 3 plus. Now let's move on to the next question. Now they want us to identify B, C, and D. So let's take a look at what they did first. Right? So they conducted an experiment. So we have to first of all figure out what it was that they did. So they took A3 plus ion solutions, reacted with a little bit of sodium hydroxide, and formed a precipitate B. Right, this was a precipitate, which was green in color. And then, when they further reacted with excess sodium hydroxide, they formed C, which was a aqueous solution, which was again green in color. Right, so they say the green color precipitate dissolves to form a green color solution called C. That was our green color solution. Right. And now, afterwards, in the last step, they say that the green color precipitate B that we have over here was separated and then it was heated. So when it was heated, when the green color precipitate was heated, it formed D, another solid, which was again green in color. Now we have to ask what these chemical compounds are. So we know A was chromium 3+. We know A was chromium 3+. So I will write a similar diagram here. We have chromium 3+, which is our A. If you react it with sodium hydroxide, you will form chromium hydroxide precipitate, which is going to be formed in the presence of sodium hydroxide, which is a green color precipitate. This is our B, chromium hydroxide. And chromium hydroxide, when reacted with excess sodium hydroxide, what do we form? We form CrOH4 minus aqueous ions. This is a complex ion which happens to be green in color. This is our C. That is our C. And finally, they have separated out a portion of the precipitate, or they have removed the precipitate and dried it, and then afterwards they heat it until it undergoes a chemical reaction or decomposition that forms Cr2O3, chromium oxide. Chromium oxide happens to be, again, a green color solid, which is our D. So students, these are the compounds that are denoted by A, B, C and D. A is chromium 3+, B is chromium hydroxide, and then we have C, tetrahydroxidochromium 3 ion, and then we have chromium oxide as our D. So these are our A, B, C and D compounds or chemical species. Right. So after identifying these, we can now move on to the next question. Write the balanced chemical equation for the reaction that takes place when a portion of B is heated. So we had a B precipitate which was used to, we had a B precipitate which we heated and obtained D. So what was B again? B was CrOH thrice, which is going to be our solid precipitate, and then we have Cr2O3 formed here, chromium oxide. So students, to balance things off first, you have to first of all balance the chromiums, and at that point you can see when you write 2 chromium hydroxides on the left hand side, you have altogether 6 oxygens. Out of the 6 oxygens, 3 oxygens are already accounted for when it comes to chromium oxide. So there are 3 remaining oxygens. We can write the oxygens here in the form of water, because that is where the oxygen is going to be included. So to get 3 oxygens, if I write 3 water molecules, you can see the hydrogens are automatically balanced. There are 3 hydroxide groups in 1 chromium hydroxide. There are 2 chromium hydroxides, so therefore altogether 6 hydrogens are present. And then in 3 water molecules, 6 hydrogens are also present. So therefore this equation is balanced. We can indicate the state symbols here. This is also solid. Water will be produced as a vapor or gas. So this is going to be a green color solid. This is also a green color solid. Right, students, this is the balanced chemical equation for the reaction mentioned in the previous question. Now we move on to the fourth question. D reacts with hydrogen peroxide in strong alkaline medium and forms an oxyanion. Not just any ion, an oxyanion. Identify the oxyanion formed. Write the balanced chemical equation for the formation of the above mentioned ion, or for the reaction mentioned above. So they want us to first of all identify the oxyanion that is made, and then actually move on to write the balanced chemical equation as well. Now students, we have already learned about a reaction where chromium 3 plus ions gets converted into chromate ions. So when it comes to the chromium oxide precipitate reacted with hydrogen peroxide in strong alkaline medium, the same reaction happens, because the oxidation state of chromium oxide, or the chromium's oxidation state of chromium oxide, also happens to be +3. So it gets converted from +3 to +6 when it is reacted with hydrogen peroxide in strong alkaline medium. So we have this reaction. I hope you remember we discussed this question a little while back. We have 2Cr3 plus along with 3 hydrogen peroxide and 10 hydroxide ions. It turns into 2 chromate ions and 8 water molecules. This was the reaction that we wrote a little while ago. Now students, one other very important details that I want you to keep in mind is, we can start this reaction with chromium 3 plus or chromium hydroxide, or we can use the chromium complex that it forms with hydroxide ions, or chromium oxide. In all of these chemical species of chromium, we see the oxidation number of chromium is +3. In all of these, the oxidation number of chromium is +3. So therefore, if you react them with hydrogen peroxide in strong alkaline medium, what you obtain is a chromate ion. We'll get the chromate ion. So we can start this reaction from anywhere. We can start from chromium 3 plus, chromium hydroxide complex, or chromium oxide. Either way, you are leading to the same answer. Now students, imagine I had to write the same equation starting from chromium hydroxide, right? So we would start writing like this, chromium hydroxides. So the chromium 3 plus ions are now in contact with 3 hydroxide ions. That's why we have written it like chromium hydroxides. So we can now write it like this. Now, do I write 10 hydroxide ions? No. To form chromium hydroxide, I would have borrowed 6 hydroxide ions from 10 hydroxide ions. So what is remaining is going to be 4 hydroxide ions. And still the answer, or the products that are formed, are the same. So you have 4 to minus along with 8 water molecules. So this is the reaction for when we start the reaction with chromium hydroxide, and if it reacted with hydrogen peroxide in strong alkaline medium, this is a reaction or balanced chemical reaction for that situation. And then now imagine if you take chromium hydroxide and heat it, you produce chromium oxide along with water. How many water molecules? Exactly 3 water molecules. Now, what we just did here was writing this chromium hydroxide in a different form. Because as we know, if you heat chromium hydroxide, we get to chromium oxide. So we can think of it that way and write down chromium oxide as a product that is formed when chromium hydroxide is heated. This is just for balancing purposes. This is not what exactly happens. However, it is easier for us to think like that when it comes to balancing this equation. Now students, you can see there are 3 water molecules on the left hand side as well as 8 water molecules on the right hand side. So water molecules being present on both sides is not ideal, so we can actually cancel off water molecules there. So at that point you will obtain this equation where you have Cr2O3 reacting with 3 hydrogen peroxide and 4 hydroxide ions, turning into 2 CrO4 2 minus along with 5 H2O. So we can double check if the number of hydrogens and oxygens are correct here. You can see there are 6 hydrogens here and there's 4 other hydrogens, altogether 10 hydrogens. On the right hand side we have 10 hydrogens. And when it comes to oxygens, there are 3 oxygens here and then there's 3 into 2 oxygens here, which is 6 oxygens here, altogether 9 oxygens, and 9 plus 4 is going to be 13 oxygens. On the right hand side we have 8 oxygens in 2 chromate ions. 8 plus 5 is again going to be 13 oxygens. Oxygen number is balanced. We can see the chromium number is also balanced. So this is your balanced chemical equation when chromium oxide reacts with hydrogen peroxide in strong alkaline medium. Now with that, let's move on to the next question. We have answered both. Identify the oxyanion form. Oxyanion formed is chromate, right? So we can write that here. Oxyanion that is formed is CrO4 2 minus aqueous, which is a yellow color ion. And then we have write the balanced chemical equation, which we have written down over here. With that, we can move on to the next question. Now we are in the third question. Let's focus on the third question here. The following observations were made regarding a salt formed with the metal X. When the salt of X was dissolved in water, a blue color solution was formed. So when this salt is dissolved in water, they are saying the solution turned blue. So which means the metal X, since that is the focus of this question here, metal X might be forming a colored solution when it is present in the aqueous medium as a cation. Meaning metal X could be a transition metal. So the cation that is in the aqueous medium is a transition metal cation. And the color of it was blue. So what are the transition metal cations that are blue in color? You immediately think of copper 2+. Copper 2+ aqueous ions or copper 2 plus ions in aqueous medium happen to be blue in color. And then they move on to the next step. They say when excess ammonia was added to the above formed solution, a dark blue color solution was formed. Yes. So as you know, if it was in fact copper, if you react copper 2 plus aqueous ions with excess ammonia, what is the result? We form a tetraamine copper 2 complex, which is a dark blue color complex. But it could be other complexes as well. For example, there are some other metal ions that will react with excess ammonia to form a dark blue color complex, such as nickel 2 plus. Nickel 2 plus will form a hexaamine nickel 2 ion complex. However, although it is also a dark blue color complex, nickel 2 plus aqueous ion solutions are not blue. Nickel 2 plus aqueous ion solutions are green. But these green color solutions, when they react with excess ammonia, they turn into a dark blue color. So although hexaamine nickel 2 ion complex is dark blue, the initial ion solution is not blue. It is green. So therefore, nickel can be ruled out. So we are still staying with copper. When concentrated HCl is added to an aqueous solution of the salt X, a yellow color, this is very important, a yellow color solution was formed. So yes, we know copper 2 plus aqueous ions can react with chloride ions or can form dative covalent bonds with chloride ions to form a tetrachlorido copper 2 ion, which is a complex ion, which happens to be yellow in color. And then we have solution formed in question 3 above is diluted with water and added and then treated with H2S. A black precipitate was formed. So keep in mind, in the solution 3 above, we had HCl. So the medium is acidic. And in acidic medium, we have added H2S. So according to our cation analysis, group 2, we know in acidic medium, the sulfide ion concentration is quite low. At low sulfide ion concentrations, if a metal cation can form sulfide precipitates, there are only a few metal cations like that. Copper is one of them. Nickel is not one of them. So they're asking you to identify X and then write the balanced chemical equations for the reactions from 1 to 4. So we need to write the balanced chemical equations for the reactions from 1 to 4, as well as we have to identify what X is. So let's move on to this question step by step. So first point was when salt of X was dissolved in water, a blue color solution was formed. So we are talking about a metal called X. It is having a salt that is dissolving in water to form a blue color solution. So the salt of metal X, let's say it is present as this. A indicates the anion. So when you dissolve it in water, you will form, let's say, X, whatever the N plus, and A, N minus. Basically, it will form a cation and an anion. And the cation happens to be having a color which is blue. So students, what cation solution that we know of is blue? Copper 2 plus. So the metal that we are talking about here, X, could be copper. But we have few other tests to confirm whether X is copper. For the time being, we are assuming X could be copper. And then in the second test, they are saying when excess ammonia is added to the above formed solution, they formed a dark blue color solution. Now actually, copper 2 plus aqueous ions can react with 4 ammonia ligands to form Cu NH3 4 times 2 plus. So we'll write the aqueous, or we'll write the state symbols as well. All are in aqueous medium. Copper 2 plus aqueous ions are pale blue in color. What is the color of tetraamine copper 2 ions? So this is tetraamine copper 2 complex ion. So this is going to be dark blue in color. This is dark blue in color. So this is the equation, balanced chemical equation for the reaction that is happening in this situation. And if you move on to the previous question, so we'll write the balanced chemical equations here itself. It will be easier for us. We'll write the equations here. It will be easier for us at that point to compare. So if you take copper 2 plus aqueous ions, copper 2 plus aqueous ions actually will have 6 water ligands getting attached to it to form this complex. So we have copper 2 plus aqueous ions reacting with 6 water ligands to form a hexa-aqua copper 2 complex ion. So what we observe to be blue in color is this complex. Actually, it is pale blue. It's a pale blue color complex. So this is the reaction for that complex formation. Copper 2 plus ions, 1 copper 2 plus ion actually react with 6 water ligands and form hexa-aqua copper 2 complex ion. And then we came across this. At the same time, students, while we learn the balanced chemical equation for this reaction, we have to also keep in mind that there's another reaction that will form a dark blue color solution. If you take nickel 2 plus aqueous ion solutions, if they react with excess ammonia, if nickel 2 plus ions react with excess ammonia, it can also form a dark blue color complex. In this complex, the formula is given here, hexaamine nickel 2 ion, which also happens to be a dark blue color solution. It's also an aqueous ion. However, the reason why we are ruling this particular complex out is because nickel 2 plus aqueous ion solutions are green in color. In this question, they very clearly mentioned when we are starting off, the salt that is dissolved in water happen to be blue in color. So if you take a salt that contains nickel 2 plus ions and you dissolve it in water, nickel 2 plus aqueous ion solutions will appear green in color, not blue. So therefore, we cannot consider nickel 2 plus aqueous ions in this particular question. So although nickel 2 plus aqueous ions will react with excess ammonia to produce a dark blue color complex, it is not going to be our answer. Our answer is going to be this. This is our answer. In the third point, they say when concentrated HCl is added to an aqueous solution of X, a yellow solution was formed. So an aqueous solution of X, now we know it is copper, aqueous solution of X has copper 2 plus aqueous ions. And if it reacts with chloride ions, or if it comes into contact with chloride ions, actually it will react with 4 chloride ligands to form a tetrachloro or tetrachlorido copper 2 ion. Tetrachlorido cuprate, not copper, tetrachlorido cuprate 2 ions. So this tetrachlorido cuprate 2 ion happens to be yellow in color. Tetrachlorido cuprate complex ion happens to be yellow in color. This is blue in color or pale blue in color. But when you react copper 2 plus aqueous ions with excess chloride ions, it will form a tetrachlorido cuprate 2 ions, which is going to be a yellow color solution. So this is the balanced chemical equation for that. They're asking you for the equation and what the yellow color species would be. So the yellow color species that is giving us the yellow color in the aqueous medium is due to this particular chemical species, CuCl4 2-. But apart from that, students, keep in mind there are other ions that will react with excess, or that will react with chloride ligands to form a yellow color solution. For example, if you take Fe2 plus, when they react with chloride ligands or chloride ions, they will form FeCl4 2-. Again, this is also yellow in color. And then we have nickel 2 plus. Aqueous ions with chloride ions will form NiCl4 2-, which also happen to be yellow in color. So these two are also yellow in color. However, Fe2 plus aqueous ion solutions are going to be pale green. When it comes to nickel 2 plus ions, it is going to be green in color. So both of them will not be our answer, because the aqueous ion solutions of Fe2 plus and nickel 2 plus is not green, because aqueous ion solutions of Fe2 plus and nickel 2 plus is not blue. Both of them are green. They are not blue, both of them are green. So therefore, we can't consider these two reactions to be the reaction that is happening here in this particular question. The answer to the reaction that is happening in this question is given here. So this is the reaction that actually takes place. Copper 2 plus ions react with chloride ions to form CuCl4 2- or tetrachlorido cuprate 2 ions. Tetrachlorido cuprate 2 ions are formed, which is yellow in color. Let's move on to the fourth part of this question. The fourth part of the question, they are saying that the solution formed in the previous part, which is CuCl4 2- solution, is reacted with H2S after diluting the solution. They say when the solution formed in question 3 above is diluted with water and then treated with H2S, a black precipitate was formed. Now we need to write an equation for this. So students, in question 3 what we formed was CuCl4 2-, and it is going to be reacted with, or it's going to be diluted with water. So when you add a lot of water, what is going to happen is the chloride ligands will be replaced with water ligands. So you're going to have Cu H2O 6 2 minus along with 4 chloride ions. So we can call it hexaaqua copper 2 ions. And then after we form this hexaaqua copper 2 aqua, copper 2 ion complex is going to react with H2S, right? So as you know, students, when it comes to copper 2 plus ions are found in group 2 of qualitative analysis of cations. As you know, in group 2, we are reacting metal cations with a low concentration of sulfide ions. So in the qualitative analysis of cations, group 2, all the metal cations that are forming sulfides can form sulfides with even low concentration of sulfide anion. So in the acidic medium, if you react H2S, you'll be able to precipitate out copper 2 plus ions as copper sulfide. So why do I say that this is happening in acidic medium here? In the third reaction, we saw copper 2 plus ions were reacted with HCl. So in the third reaction, the medium was made acidic. In the fourth reaction, we didn't add a base to remove this acidity from the medium. We only diluted the medium. So the medium is still acidic. So in the presence of an acidic medium, copper 2 plus ions can react with H2S to form copper sulfide, CuS. So this is your black color precipitate. And the water molecules will be removed from the complex. So there will be 6 water molecules coming out and there will be 2 H pluses released as well. So this is the equation for the reaction that is happening in the fourth step of this question. Now students, let's move on to the next part. So now we are at the fourth question. In the fourth question, you can see that there are some tests that are being done and there are some observations that go along with the tests. As you can see, the question, let's first read the question, students. S is a solution formed by dissolving 2 3D transition metal chlorides. So there are 2 3D transition metal chlorides. So that is very important to notice. There are 2 3D transition metal chlorides. Now, they are saying the very first test is sodium hydroxide is added to an aqueous solution of S. A blue-green precipitate was made. Have you ever come across a blue-green precipitate? Not really. We have not necessarily studied a precipitate that is blue-green in color. We have looked at blue color precipitates as well as green color precipitates separately. We have a blue color precipitate, especially when it was we see sodium hydroxide reacted with copper 2 plus aqueous ions normally produces a blue color precipitate, copper hydroxide. And we have learned about a few green color precipitates such as nickel hydroxide, Fe or 2 plus when reacted with sodium hydroxide forms ferrous hydroxides, and chromium hydroxide. Cr3 plus reacted with hydroxide ions forms chromium hydroxide, which is also green in color. But we haven't come across a blue-green precipitate. This indicates S contains 2, as mentioned, 2 3D transition metal cations. One could be copper 2 plus, others could be Fe2 plus, Ni2 plus, or chromium 3 plus. S was heated with sodium hydroxide and H2S. Now students, we are very familiar with this particular reaction. What is the reaction? When you are reacting the chemical species with hydrogen peroxide in strong alkaline medium, you should immediately think of chromium 3 plus ions. When chromium 3 plus ions were reacted with hydrogen peroxide in strong alkaline medium, what happened? We saw an oxyanion being formed. What is the name of the oxyanion? Chromate ions. So, and chromate ions were yellow in color, and we can very clearly see that observation. A yellow color solution was formed. When you are heating S with sodium hydroxide and H2S, or when you are heating S with sodium hydroxide and H2O2, hydrogen peroxide, you are forming a yellow color solution. But at the same time, there was a precipitate formed as well. Right? So there is a precipitate formed that did not get dissolved as the reaction proceeded. So again, we know the blue color of this blue color precipitate would have been formed, let's say, due to copper 2 plus. There's a green color precipitate as well. Green color could have been so many things. If it could have been Fe2 plus, nickel 2 plus, or chromium 3 plus. But with this observation, where when you react it with hydrogen peroxide and sodium hydroxide, a yellow color solution was formed. This is due to formation of chromate, or could be due to the formation of chromate. So what could be present in the medium other than copper 2 plus? So we are somewhat developing an idea that the two ions could be copper 2 plus and chromium 3 plus. We are not quite sure yet. We need to see some confirmations for that, but we are somewhat sure that chromium 3 plus and copper 2 plus are the ions that are present in the medium. And the precipitate that still remained could be copper hydroxide. It could be copper hydroxide. Now let's move on to the C part. To the precipitate formed in B, a small volume of HCl was added. A small volume of concentrated HCl was added. A yellow color solution was formed. So if it was copper, can copper 2 plus ions react with HCl to form a yellow color solution? Yes. Tetrachlorido-cuprate-2 complex, which we looked at in the previous question. But we are talking about the precipitate that was formed, which is copper hydroxide. So copper hydroxide, can it dissolve in hydrochloric acid to form this complex? Yes. So therefore, this observation confirms that copper was there. So the yellow color solution that is formed here is this. The yellow color solution that is formed is CuCl4 2 minus. The solution formed in C was reacted with H2S. A black color precipitate was formed. The solution formed in C was reacted with H2S. And a black color precipitate was formed. So you know very well, as I mentioned earlier, when it comes to acidic medium, if you react a cation in acidic medium with H2S, the metal sulfides can be formed when it comes to metals found in group 2 of cation analysis. So therefore, what we have here is copper sulfide that is formed. We know copper 2 plus ions will react with H plus in acidic medium. As you know, copper 2 plus will react with H2S in acidic medium and can form copper sulfide, which is a black color precipitate. So now we have developed an idea about what chemical species are getting formed, as well as what are the two main ions found in this medium. So what are the cations present in solution S? So that's the very first question. So we'll write it down here. what are the cations present in solution S. So according to our observations, according to the details we obtained from this table, we can say we have copper 2 plus, we have Cu2 plus ions, and we have chromium 3 plus ions. That is our answer for that question. And then we have the next one. What is the reason for observing a yellow color supernatant in B? So we saw here, when it comes to the reaction that we did here, S was heated with sodium hydroxide and hydrogen peroxide. A yellow color solution was observed, and then we had a precipitate as well. So let's see that situation here. So we have our aqueous ion solution, which would have contained copper 2 plus along with chromium 3 plus. And as you heat it with H2O2 in strong alkaline medium, we saw the following reaction. We saw that there's a small precipitate that is formed here, and the solution was yellow in color. And as you see hydrogen peroxide in strong alkaline medium reacting with something, you should immediately think of the formation of chromate starting from chromium. So chromium 3 plus ions would have turned into CrO4 2 minus. So this chromate ion is the reason for the yellow color of the solution. What would have been formed here? In the medium, apart from chromium 3 plus, there was copper 2 plus ions. Copper 2 plus ions don't get oxidized in the presence of hydrogen peroxide. So therefore, what would have been formed here? We are doing this reaction in strong alkaline medium. So therefore, copper would react with the hydroxide ions present in the medium and would have produced copper hydroxide. And what would have been the color of the precipitate? A blue color. Actually, you can call it a pale blue color as well, because copper hydroxide precipitate appears to be pale blue in color. Right. Now, let's move on to the question again. So, what is the reason for observing a yellow color in the supernatant of part B? Because we are forming chromate, CrO4 2 minus aqueous ions. So this is the reason for observing a yellow color in the medium. In the next question, they're asking, what is the chemical species responsible for the yellow color observed in the solution formed in C? C is this. So let's take a look at C. To the precipitate formed in B, which is copper hydroxide, a small volume of HCl was added. So then what happens? If you take the precipitate out and if you reacted it with HCl, so we have CuOH twice reacting with 4HCl, you will form this complex CuCl4 2 minus, which is yellow in color. And you can see two H pluses will react with two hydroxides to form two water molecules, and the remaining H pluses will be seen on the product side. So this is going to be your reaction. You will convert a solid that we have here. We'll write the state symbols as well here. We can see that copper hydroxide, the green copper hydroxide, which is a blue color precipitate, pale blue color precipitate, turns into a yellow color solution in the presence of HCl. They're asking you, what is the chemical species responsible? The chemical species responsible for the yellow color in solution C is going to be this CuCl4 2 minus AQ or aqueous. This is the chemical species responsible for the yellow color in the aqueous medium. Let's move on to question 4. Write the balanced chemical equation for the reaction that takes place in B and C. We have already written that once, but we can write it again because the question asks us to do so. So it's very simple. When it comes to chromium, of course, we have written this equation about 3 to 4 times in this particular lesson itself. So we can write 2Cr3 plus 3H2O2 plus 10OH minus turns into CrO4 2 minus and 8H2O. So this is the equation for equation that is happening at B. Chromium 3 plus ions are turned into chromate ions. Apart from that, in B, we also see the formation of a precipitate. That precipitate is formed due to copper 2 plus ions reacting with 2 hydroxide ions to form copper hydroxide. So these are the two reactions that are happening when it comes to B. Both of them are for B. And then we have, let's say, to a small portion of copper hydroxide, we are going to be adding HCl. We just wrote that equation, we'll write it again. So we have CuOH 2 reacting with 4HCl turning into CuCl4 2 minus plus 2H2O, and apart from that you will see 2H pluses remaining here as well. And this is the reaction that is happening at C. So you should be able to note down this kind of reactions without much difficulty by now. With that in mind, we can move on to our next question. In the 5th question, they're asking what observations you would expect when acidifying the supernatant solution formed in B. So we have a yellow color solution formed in B, and we know what that yellow color solution was. That is a chromate solution. They're asking what observation you would expect. Now students, you should keep in mind the following reaction. Chromate, which is yellow in color, can be turned into dichromate, and chromate ions are normally observed in alkaline medium. Dichromates are normally observed in acidic medium. Normally, we write this equilibrium between chromate and dichromate. There's a equilibrium like this. Take a look at the equilibrium. CrO4, 2 minus. Actually, we'll be using 2 chromate ions. Turns into Cr2O7, 2 minus, which is a dichromate ion. So this is the equilibrium that is observed between chromate and dichromate. Chromate ions are yellow in color, and dichromate are orange in color. This is something that you should always keep in mind. So, as you know, if you increase the acidity of the medium, equilibrium will be shifted to the right hand side, producing more of the dichromate ion, which is going to make the solution appear orange. If you add a base to the medium, H plus will react with the hydroxide ions from the base, and H plus concentration will go down. As H plus concentration goes down, equilibrium will shift to the left hand side, producing more and more of our yellow color chemical species, which is chromate ion. So in alkaline medium, as you start making a chromate or dichromate solution more and more alkaline, the most prominent color you're going to observe is yellow. If you take a chromate solution and start making that solution more and more acidic, as H plus concentration goes up, equilibrium will be shifting to the right hand side according to Le-Chatelier's principle, and will be producing our orange color dichromate ion. So this is the equation for that reaction. Right, students, now we are at the 5th question. In the 5th question, they are asking us to write the IUPAC names of the following. So when you're writing IUPAC names, there are a few rules that we follow. You would have learned about it in theory. So let's take a look at each of these compounds and try to learn their names. Now, first one, we have a positively charged complex ion and a negative ion. So what is the positively charged complex ion that we have? Cu NH3 4 times. And obviously, since there are 2 hydroxide ions, the overall charge over here would be 2 plus, and then we have 2 hydroxide ions. So if you break this main compound into its ions, we have a complex ion where copper and ammonium ligands or ammonia ligands are together, and then we have hydroxide ions. So this copper ammonia complex can be named the following way: tetra amine. So when you write amine, you have to have 2 M's or double M. And then since it's a positively charged ion, we can straight away write the name of copper without adding ATE at the end. If it's a negatively charged complex ion, we would have to add ATE at the end. So since it's a positively charged ion, we can write tetraamine copper. Since the overall charge of the copper is +2, we can write, actually you can see amine groups are neutral in charge. Amine ligands are neutral in charge. So therefore, this positive charge that we see over here, +2 charge, is due to the charge of copper ion here. So therefore, we can write 2 over here because the oxidation number of copper here is 2. Tetraamine copper 2, and you will leave a space, and then we can write the negatively charged ion's name, which is hydroxide. So the name would be tetraamine copper 2 hydroxide. This is how it will be named. And then we have again a similar situation. We have the copper ammonium complex and then together with bromide ions. So we'll break it down into its ions. We have Cu NH3 4 times. So since there are 2 bromide ions, the charge over here would be 2 plus, and we have 2 bromide ions. So we learned how to write the name of this complex. We will rewrite it again here. It's going to be tetraamine, and we have copper here, COPPER, tetraamine copper 2. We have a bromide ion here, so tetraamine copper 2 bromide. Tetraamine copper 2 bromide. So this is how you would write a name for IUPAC name for a compound like this. And then we come across a negatively charged complex ion. So when it comes to negatively charged complex ion, the ion's name should end in ATE. You shouldn't forget that. So we have 4 chlorine or 4 chloride ligands. So we write tetra to indicate the number of chloride ligands, and then comes the name of chloride ligand, which is chlorido. You might see in certain scientific literature, they will also refer to this chlorido ligand as chloro, but we are going to be using chlorido, tetrachlorido, and then we have copper. So what is the oxidation number of copper here? So here we have 4 chloride ligands along with 1 copper. We don't know the charge of the copper, let's say. And overall charge here is -2. That means 2 of the chloride ligand's charge has been removed or neutralized by the charge on the copper. So copper would have been +2. That's one way to think of it. So we have here copper with the oxidation state of +2. So the name would be tetrachlorido copper, or can we call copper here? Since it is a negatively charged ion, we will call it cuprate, as the name should end in ATE. Tetrachlorido cuprate 2. Oxidation state of copper here is 2 ion. Tetrachlorido cuprate 2 ion is the name. And then we have another complex ion which is negatively charged connected to a cation here. So let's take a look at the 2 main ions that are formed here. We have copper and we have FeCN6. Now students, we don't know the charge. So imagine when it comes to Fe, it can have Fe3 plus or Fe2 plus. Imagine this was Fe3 plus. Then with the Cn ligands, since Cn ligands are negatively charged, since there are 6 of them, they will all bring in 6 negative charges. Altogether, the overall charge of this cation at that point should be -3, which would in turn mean that these copper ions should have an overall charge of +3, indicating each copper ion should be 1.5 plus in charge, which does not happen. So copper cannot have 1.5 plus charge. So therefore, this situation cannot happen. However, if you take this situation where Fe, where you have the same compound but we are now writing this compound again to indicate that Fe2 plus is the oxidation state, or 2 plus is the oxidation state of Fe here. So if we have a ferrous ion instead of a ferric ion, then what would happen? Still, Cn ligands will bring in altogether 6 negative charges. So the overall charge of the entire complex ion would be -4. So the overall charge would be 4 minus, which would mean that 2 copper ions should bring in a +4 charge, which indicates each copper ion should have a +2 charge, which is possible. So therefore, what we're dealing with is this. Cu2 plus is the oxidation state of copper that we see here. And when it comes to FeCN6, the overall charge of that complex is going to be 4 minus, and the ion that we find here is at +2 oxidation state. So how do we name such a thing? How do we name this compound? So if we erase this part, since it is not how it is happening, we can write the name here very clearly then at that point. So we know we have copper at +2 oxidation state, Fe2 plus also at +2 oxidation state, or Fe at +2 plus oxidation state. So then the name would be written in the following manner. We would write copper, since copper is a positively charged ion found here and it is having +2 oxidation state, we would write copper, and then we'll leave a space, and then we have 6 Cn ligands, so we can write hexa cyanido. As you can see, this entire ion is negatively charged ion, FeCN6 4 minus, but the oxidation state of Fe was +2. So after writing hexacyanido, we have to make sure when you are writing the name for Fe that the name ends in ATE, and at the same time you have to mention the oxidation state of ion. So over here you are not going to write hexacyanido ion, instead we are going to write hexacyanido ferrate. Hexacyanido ferrate 2. Since this is a compound name, we don't have any other part to the name. It's copper to hexacyanido ferrate. So this is how you would write the name for a compound like this. Now students, we are done with the questions revolving around practical 23. We started off with discussing the theory parts revolving around practical 23. We moved into the lab afterwards, did all the experiments, observed the color changes that take place, and then we came back to do some questions. I hope with the questions that we have done, you have learned how to apply the theory that you learned into questions. With that, I will conclude our experiment 23, and we will meet again in the next video.